I think I messed this up. That's okay. Maybe. I don't know. Come back in the stream and it's like, I'm not even here, man. What the heck?
But in all these instances, we're talking about the same kind of molecule. And these molecules that we're calling carbohydrates, they do some pretty incredible and pretty hugely necessary things in our bodies and in most living things for that matter. And maybe one of the most familiar of these tasks is the fulfillment of our body's energy source. So carbohydrates fulfill our body's energy needs. And the main energy source for metabolism in our bodies is glucose. So glucose, and I bet you've heard of glucose before, if water. And because these biological molecules are hydrates of carbon, you can find them fitting into the general formula C, so a number of carbon atoms. So N for just kind of a generic number of carbon atoms, and then a matching number of water molecules, so H2Os, usually in the exact same number as your carbon atoms. And because all of these carbons kind of have an associated water, you can think of this as being essentially a 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen. Now, when we have one of these carbohydrate molecules, we call it a monosaccharide. So monosaccharide. And monosaccharide essentially means one saccharide. And saccharide molecules, so H2Os, usually in the exact same number as your carbon atoms. And because all of these carbons kind of have an associated water, you can think of this as being essentially a 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen. Now, when we have one of these carbohydrate molecules, we call it a monosaccharide. So monosaccharide. And monosaccharide essentially means one saccharide, and saccharide is a synonym for carbohydrate. So saccharide is actually, it's derived from the Greek word for sugar. So you might hear a single carbohydrate referred to as a simple sugar. But in all these instances, we're talking about the same kind of molecule. And these molecules that we're calling carbohydrates, they do some pretty incredible and pretty hugely necessary things in our bodies and in most living things for that matter. And maybe one of the most familiar of these tasks is the fulfillment of our body's energy source. So carbohydrates fulfill our body's energy needs. And the main energy source for metabolism in our bodies is glucose. So glucose, and I bet you've heard of glucose before. If you might have heard it in the context of checking blood glucose levels for people with diabetes, but glucose is a monosaccharide made of 6 carbons. And you might also be familiar with kind of the structural rigidity of cell walls in plants. And that rigidity comes from the rigid carbon backbone of several carbohydrates linked together to form the polysaccharide. So polysaccharide, several saccharides, several carbohydrates linked together, and we call that cellulose. So cellulose is the polysaccharide, the carbohydrate that makes up the structural backbone of cell walls. And then, of course, one of the most beautiful carbohydrate roles in my mind is the use of ribose, which is a 5-carbon sugar that supports the transcribed products of our genes in RNA. And so you might have caught on that in all 3 of the carbohydrates that I just mentioned, we see the ending ose, O-S-E. And we see that in glucose, cellulose, and ribose. And that's because ose is the suffix for sugars. And there are actually 2 prefixes that help us further break down the naming of these compounds. And so the first prefix that we're going to consider is how many carbons are in the chain. So the number of carbons that are in the chain for this molecule. So for example, I'm going to draw glyceraldehyde, which is kind of generally considered to be the simplest carbohydrate. And it looks like this. And if this carbonyl group right up here was just another hydroxyl group, this would be glycerin, 3 carbons but with 3 hydroxyl groups. But instead it's an aldehyde. And so this molecule is for that reason named glyceraldehyde. And the aldehyde is our functional group. And so if we're going to count how many carbons are in this molecule, we'll start with our functional group carbon, this carbonyl carbon up here, and we've got 1, 2, 3 carbons in glyceraldehyde. And so there are 3 carbons, and for that reason we would call this a triose. Tri for 3, and again, os as our suffix for sugar. And if we added a 4th carbon, we would call it a tetrose. So 4 carbons in a carbohydrate chain is a tetrose. And then we add a 5th carbon, and that would be a pentose. So pentose for 5. And if we added an additional carbon, we would have 6 carbons, and that would give us a hexose. Hex being the prefix for 6. And I mentioned before when I was talking about the energy source of our body that glucose is actually a 6 carbon carbohydrate. And so as an example of a hexose, I'll draw glucose here. So this carbon chain, there's 6 carbons. We've got 1, 2, 3, 4, 5, 6 carbons, and this is a hexose called glucose. Now, in the case of glucose, the functional group is an aldehyde, just like our glyceraldehyde. So the functional group up here is an aldehyde. But what if we make it a ketone? You see, we can actually make it a ketone and still retain that 1:2:1 ratio. And it brings us kind of another pretty popular hexose called fructose. So this is another hexose. It still has that 1:2:1 carbon, hydrogen, oxygen ratio, but instead of having the aldehyde functional group, it has a ketone functional group right here. And so that brings up kind of the second naming prefix. We have to indicate whether we're working with an aldehyde or a ketone. So glucose would be more accurately referred to as an aldohexose. And that aldo is a reference to the fact that the functional group in this carbohydrate is an aldehyde. And fructose, then on the other hand, let me write fructose down. So fructose is a ketohexose. And again, the keto is a reference to the fact that the functional group here is a ketone. And then if we want to just kind of exhaust this kind of second prefix idea, going back up to glyceraldehyde, which we said was a triose, because the functional group is an aldehyde, this would be an aldotriose. So aldotriose. So we name based on length of the carbon chain, the number of carbons that are in the chain, and the functional group that's in our carbohydrate. And the last kind of major component of naming is the stereochemistry of the highest numbered chiral center. So again, we start with a carbonyl carbon, and if we use a Fisher projection like we did with glucose, then we go to the highest chiral center, which would be this last one, and we decide the stereochemistry of that chiral carbon. And just kind of as a shortcut with Fisher projections, if the kind of highest substituent in this case, the hydroxyl group is on the right-hand side, then it's an R stereochemistry. And if it's on the left side, it would be an L stereochemistry. So let me try to make that a little bit easier, and I'll just kind of redraw glyceraldehyde, a nice small molecule, as a Fisher projection. So we've got our aldehyde, and then we've got kind of our next 2 carbons in the chain, 3 carbons, and we have 1 chiral center in this carbohydrate, this one right in the middle here. And our OH group, you can see, is on the right-hand side. So this is an R configuration. And for carbohydrates, actually, a lot of the naming is associated with the guy Fisher who invented these Fisher diagrams. But he decided, since it was an R, and the Latin for right-handed kind of is dexter, we assign a D to this configuration. And then if we kind of drew this in a mirror image, and we drew the enantiomer of it, and we had our aldehyde carbon up here, and our last 2 carbons and their hydroxyl groups. Now we see that the chiral carbon, the highest numbered chiral carbon, has its primary substituent on the left side at the bottom of this Fisher projection. And so this would be assigned an L, which is a little bit easier. And so as an example, I guess going back to the glucose, this would be a D aldohexose, because the hydroxyl group is on the right-hand side of this molecule. And again, with our fructose, same thing. The last chiral carbon has the OH group on the right-hand side, so this is a D ketohexose. Now, before I move on, I want to allow you to review Fisher diagrams because I know I just kind of blazed through it, and really they're important, especially with carbohydrates, because stereochemistry becomes quite important in the biological implication of carbohydrates. So I included a great video by Jay with Khan Academy on Fisher projections, and it's actually the video I used to learn about them. So I'd encourage you to kind of pause here for a second and give that video a watch on Fisher projections and get real comfortable with absolute configuration, and then we'll move forward with the discussion of carbohydrates. Okay, so we spend a lot of time on the front end of carbohydrates talking about their stereochemistry, especially
Unless it's here somewhere, maybe. Ah, it's here.
especially of that last chiral center. And again, it's because it plays a large role in the biological function of these molecules. For example, we humans are enzymatically programmed to break down and digest the D sugars. So for that reason, I want to spend at least one last short amount of time trying to clarify the questions that I originally had when learning about carbohydrates, stereochemistry, and nomenclature. So first, I need to clarify that D and L refer to stereochemistry, but they don't speak to the overall optical activity of the molecule. So as an example, let's take a look at D-threose. And D-threose has an aldehyde functional group, and it has 4 carbons, so it's an aldotetrose. But you can see that the last chiral center down here has its functional group, this hydroxyl group on the right side. So it's a D carbohydrate, D-threose. But it turns out that there are actually 2 chiral centers here, and whenever we have, n chiral centers, whatever number of chiral centers we have, then we have 2 to the n possible stereoisomers. And in this case, there are 2 chiral centers, so we have 4 possible stereoisomers. And it turns out that this particular stereoisomer actually has kind of an overall optical activity such that it rotates flame-like counterclockwise, as opposed to clockwise like you would see with most R configurations. So even though this is D, it's actually a negative. It gets a kind of a negative sign for its optical activity. So this is D minus threose. And again, it's D because this lowest chiral center here has an R stereochemistry. So it's a D carbohydrate. Now, the second big thing that I want to clarify is that it's important to note that the D and L configurations of a particular carbohydrate are enantiomers, which mean they differ at every chiral carbon, not just the last one. So we can take a look at this in the case of glucose. So glucose, again, is an aldehyde carbohydrate. So it's an aldose, and it's got 6 carbons. So it's an aldohexose. And this is the D configuration. The L configuration is going to look like this. So you can see, again, it has 6 carbons. So nothing's changing there. But as we reflect it across this mirror, every single chiral carbon is going to be the mirror image. So this is L-glucose. And again, the big thing that I want to clarify here is that it's not just this last chiral center down here. It's not just this last chiral carbon that is flipped for the D and L. The D and L glucose are true enantiomers. So enantiomers, which means that they're complete mirror images. They differ at every single chiral carbon. Now, that being said, if the D aldohexoses, these glucose, if the D and L aldohexoses are enantiomers, that means that all of the D aldohexoses have to be diastereomers of each other because they're not superimposable and they're not mirror images. And I know that's confusing, but I've drawn out here all of the D aldohexoses, and we'll just kind of take a look at what I'm talking about. So we have the D aldohexoses here, and there's 8 of them that I've drawn. So in the case of glucose up above, I'm going to flip back up to it for a second. You see that D glucose and L glucose are enantiomers. They differ at every single carbon. Now, all of these are stereoisomers but they differ at maybe just one. They don't differ at every single carbon from glucose. So here's glucose down here, and you can see D-allose. Well, it's just different at this one chiral carbon right here. Or you can see D-galactose up here. The only difference is this C4 chiral carbon from glucose. And so what you see is that these aren't mirror images and they're not superimposable. So all of the D aldohexoses are diastereomers. It's the same thing for all of the L aldohexoses. They're all diastereomers of each other. And you can carry that thought through the ketopentoses. All the D-ketopentoses would be diastereomers of each other. And they would have a partner in the L-ketopentoses that would be their enantiomer. So again, this is terribly confusing idea, but I really think the best way would be if you could just pause the video for a second and take a look at all 8 of these and notice where they're different, and notice that they're not different at every single carbon, so they can't be enantiomers. Okay, I've said enantiomers and diastereomers too many times already, I'm sure. Now, I mentioned just a minute ago that glucose and galactose are different only at the C4 carbon. Remember, we've got 1, 2, 3, 4, 5, 6, and similarly with glucose, 1, 2, 3, 4, 5, 6. So the only carbon that these differ at is this C4. And because they just differ at one carbon, we have a special word for these, and they're called epimers. So epimers are diastereomers that differ at one chiral center. And that's just kind of a vocab word that's probably going to come up several more times as you look at carbohydrate chemistry. Now you can take kind of this thought of D versus L carbohydrates to the next level with critical thinking. If you consider all of the stereoisomers for an aldohexose, again, we're talking about aldohexoses right now, and how many chiral centers do these aldohexoses have? Well, you can count. There are 1, so 1, 2, 3, 4. Now that's not numbering that. I'm just counting the chiral centers because this carbon up here, the carbonyl carbon, is double bonded to an oxygen, so it's not a chiral center. And down here, this carbon is bound to 2 different hydrogens, so it's not a chiral center. So all of these aldohexoses have 4 chiral centers, and that means they have 2 to the 4 or 16 stereoisomers. Now, half of those are going to have this OH at the bottom on the right side, and the other half would be left. So half of 16 is 8, and that's how we get to this idea that there are 8 D aldohexoses. And that's just kind of a thought that you can use, and you can translate that into pentoses. Pentoses are going to have 3 chiral centers. So there's going to be ultimately 8, and there would be 4D and 4L. So the last thing I want to do is cover just the common names for maybe the 5 most commonly seen monosaccharides. And I've similarly kind of pre-drawn their structures in, and I'll give you their names and kind of the mnemonics that I was taught to remember them by. So the first one that we have right here, number 1, is ribose. So ribose. And the way I remember this is a pentose. It's an aldopentose. It's got an aldehyde and 5 carbons. Ribose is all right. Now, the next one we can see here, because we've drawn it a couple different times, is glucose. And I should mention that this is D-glucose again, and I should mention that this is D-ribose here. But the way that I remember glucose is actually a little bit racy, so keep in mind that I do not support flipping people off with your middle finger, but if you look at this, man, it sure does resemble somebody flipping off people. So you can say, I don't know, whatever insult you want to glucose. I'll just kind of like write some kind of expletive marks here to glucose. And you can remember that glucose, we'll just pretend that we're really frustrated with it and we're kind of cursing it out. And again, I don't condone you using your middle finger, but thank goodness that organic chemistry can redeem even the most heinous of societal insults. And so we can remember that D-glucose looks like if we're holding, if kind of this is our pointer finger, and you can curl your finger up and kind of stick your middle finger out with the fingernail down towards the page, I'm sure you can make the connection of how your fingers resemble glucose. And so that's kind of my mnemonic for that. This next one is mannose, and again, it's D-mannose. And if you position your fingers in the same way that you were with glucose, and now you just extend your pointer finger as well, so now we've got kind of 2 fingers extended and then 2 kind of curled up, we can see that it's like a man holding his gun. So we're the man and we're holding our gun, and that's D-mannose, so man with a gun. And again, this is an aldohexose, just like glucose, and to keep using that vocabulary, these are diastereomers of each other. And then this next one on the list is galactose. And it's kind of lame, but the way I remember this is that D-galactose is the C4 epimer of glucose. So galactose, I've got the C4 epimer of glucose. So down here, this is the only carbon The only chiral center where it differs from glucose, so I remember it's the C4 epimer. And then last but not least, we have fructose, and this kind of made an appearance in an earlier video. So we've got D-fructose, and the way I remember D-fructose is that it's the ketose of glucose. So the ketose of glucose, and you can see that it very much resembles glucose, except that instead of an aldehyde, it has a ketone functional group. And these are maybe the most common monosaccharides that you'll see in an organic chemistry and kind of biochemistry context. Alrighty, so we've been speaking so far about carbohydrates as chains of carbon atoms. And these are chains of carbon atoms that feature an aldehyde or a ketone functional group, and that falls into this general kind of 1 to 2 to 1. To be this 1, 2 straight chain. So I'll draw glucose here. The functional group up here is an aldehyde. But what if we make it a ketone? You see we group right here. And so that brings up kind of the second naming prefix. We have to indicate whether we're working with an aldehyde or a ketone. So glucose would be more accurately referred to as an aldohexose. And that aldo is a reference to the fact that the functional group in this carbohydrate is an aldehyde. And the fructose, then on the other hand, let me write fructose down. So fructose is a ketohexose. And again, the keto is a reference to the fact that the functional group here is a ketone. And then if we want to just kind of exhaust this kind of second prefix idea, going back up to glyceraldehyde, which we said was a triose, because the functional group is an aldehyde, this would be an aldotriose. So aldotriose. So we name based on length of the carbon.
Yeah, that's okay. Go for it.
Chain, the number of carbons that are in the chain, and the 2-to-1 ratio of carbon, hydrogen, and oxygen. And of course, I'll keep using glucose as an example. Now, I've also used the term polyhydroxylated to refer to the numerous hydroxyl groups that are in these carbohydrates. And really, I bring all of this verbiage back up to hopefully spark your ability to see that carbohydrates have all the makings of an internal or intramolecular, I guess, reaction between the carbonyl carbon right here and one of the hydroxyl groups. Because essentially what we have is carbonyl and alcohol chemical reactions just kind of waiting to happen. And what happens when an alcohol nucleophile attacks an aldehyde or a ketone? Well, if there's an excess of alcohol, we end up with a product that is either an acetal or a ketal. But what happens if there's only one nucleophilic attack by an alcohol? We just have one hydroxyl groups that are in these carbohydrates. And really, I bring all of this verbiage back up to hopefully spark your ability to see that carbohydrates have all the makings of an internal or intramolecular, I guess, reaction between the carbonyl carbon right here and one of the hydroxyl groups. Because essentially what we have is carbonyl and alcohol chemical reactions just kind of waiting to happen. And what happens when an alcohol nucleophile attacks an aldehyde or a ketone? Well, if there's an excess.
Where's he at?
Oh. Yeah. Well,
of alcohol, we end up with a product that is either an acetal or a ketal. But what happens if there's only one nucleophilic attack by an alcohol? We just have one alcohol, and that's going to be the case in the ring-closing intramolecular reaction we have going on here. Well, in that case, we end up with a hemiacetal or hemiketal. And really that terminology is just kind of a review of acetal and ketal chemical reactions that would fall under, I guess, if you're looking in an organic chemistry book, aldehyde or ketone reactions, probably in the carbonyl section. So let's show how this process is happening in the context of our glucose over here. First, I'm going to highlight the particular hydroxyl oxygen that's going to act as the nucleophile. So we'll make that pink. And after being deprotonated, so after losing this proton, this oxygen is going to have an extra set of electrons right here. And those electrons are going to target that carbonyl carbon. So I'll draw the carbonyl carbon in green. And remember that the carbonyl carbon has a partial, of course I'll keep up group, and that falls into this general kind of 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen. And of course I'll keep using glucose as an example. Now, I've also used the term polyhydroxylated to refer to the numerous hydroxyl groups that are in these carbohydrates. And really, I bring all of this verbiage back up to hopefully spark your ability to see that carbohydrates have all the makings of an internal or intramolecular, I guess, reaction between the carbonyl carbon right here and one of the hydroxyl groups. Because essentially what we have is carbonyl and alcohol chemical reactions just kind of waiting to happen. And what happens when an alcohol nucleophile attacks an aldehyde or a ketone? Well, if there's an excess of alcohol, we end up with a product that is either an acetal or a ketal. But what happens if there's only one nucleophilic attack by an alcohol? If we just have one alcohol, and that's going to be the case in the ring-closing intramolecular reaction we have going on here. Well, in that case, we end up with a hemiacetal or hemiketal. And really that terminology is just kind of a review of acetal and ketal chemical reactions that would fall under, I guess, if you're looking in an organic chemistry book, aldehyde or ketone reactions, probably in the carbonyl section. So let's show how this process is happening in the context of our glucose over here. First, I'm going to highlight the particular hydroxyl oxygen that's going to act as the nucleophile. So we'll make that pink. And after being deprotonated, so after losing this proton, this oxygen is going to have an extra set of electrons right here. And those electrons are going to target that carbonyl carbon. So I'll draw the carbonyl carbon in green. And remember that the carbonyl carbon has a partial positive charge on it. It has a partial positive charge because a lot of the electron density in this double bond is being hogged by this oxygen. So the oxygen has a partially negative charge and the carbonyl carbon is partially positive. And that makes it a perfect target for the nucleophile that's been created in the deprotonation process of this oxygen. And so after the oxygen's electrons attack this carbonyl carbon, what's going to happen is the electrons from this double bond are going to kind of kick back up to the oxygen up here, and eventually they're going to attract another proton and will form another hydroxyl group out of some of the electrons from that bond. Now you might be asking, and it's a perfectly valid question, why it's this particular oxygen, the one that I've highlighted, that's acting as the nucleophile. And you're going to see as soon as I get the product drawn that we formed a 6-member ring. So it really has a lot to do with product stability. And if you remember that the basis for the formation of the ring in the first place was the increased stability over the straight carbon chain. So it makes sense that we're going to form the most stable ring that we can. Now, when we end up with a 6-membered carbohydrate ring, such as the case with glucose here, we call the product a pyranose. Pyranose, the os again as a suffix for sugar, and the pyr part to indicate that this ring is sugar with 6 carbons. And then if the carbohydrate ring is a 5-carbon ring, we call it a furanose, which is a bit easier for me to remember because furanose and 5 both start with the letter F. So that's kind of the memory jogger for me. And maybe a good example for that would be ribose with its 5-carbon chain. But I'll kind of stop there because almost every ring-forming carbohydrate that I can think of with biological implications at least forms either a 5 or a 6-member ring. So pyranoses and furanoses. So just by convention, you can see that I've placed the O in this corner up here, and that places the formerly carbonyl carbon down here right below it. And it's actually no longer the carbonyl carbon, but it's still significant because it's the only carbon here that is bonded to 2 oxygen atoms, the highlighted oxygen, and it's bonded to another hydroxyl group as well. So I'll keep it distinguished in color, and we also distinguish its name now as the anomeric carbon. So that's the anomeric carbon, and then we can go ahead and fill in the rest of the substituents in the diagram. So hydroxyl group and another, and we call this diagram a Haworth diagram. So Haworth diagram. And the Haworth diagram doesn't show us the actual configuration of the ring because in reality, 6-membered rings are going to show up in a more stable chair shape, but it is beneficial in telling us which substituents are above or below the ring. So to keep this convention straight in my mind, I remember the phrase downright uplifting. So downright uplifting, kind of a play on I guess the phrase that's downright uplifting, but downright uplifting because as I fill in the substituents, those on the right side of the Fisher diagram will point down, and those on the left side of the Fisher diagram are going to point up. So we can actually see that one's up, and we'll make sure that this number's off right. This one's up as well, and maybe we'll name this, or maybe we'll start numbering with 1, 2, 3, 4, 5, 6, and we can do that over here. This would be 1, 2, 3, 4, 5, 6. So our 3-carbon in the Haworth diagram is pointed up, and our 3-carbon on the Fisher diagram has its substituent on the left. So downright up left. And as we get to the last carbon group, which kind of forms this tail down here, I remember that if it's a D sugar, that group is going to point up in the Haworth, projection. So this is a D sugar, and you can see in the Haworth projection that this last carbon points up as well. And really this is going to be the case for a lot of sugar chemistry that you deal with because again, we're enzymatically programmed to digest D sugars. So we often end up with this last group pointing up. Now the last thing I want to show you is the chair conformation. So the chair conformation, and that's because this is a kind of diagram that's going to give us a sense for the actual configuration of D-glucose, but it really does just follow suit with the Haworth projection as far as the substituents being above or below the ring. So let me just kind of keep filling in the substituents here, and I'll number them off again, just so you can kind of see that there's some consistency here. So we've got 1, 2, 3, 4, 5, 6, And again, this 3 carbon right here is the only one with the hydroxyl group pointing up. And I guess I better change the color of our 1 carbon to keep that consistent as well. Now, I didn't indicate the position of the anomeric carbon's hydroxyl group yet, because I think it makes more sense to show it in this diagram. Remember, that the original nucleophilic attack by the oxygen, way back over here, that could have created 2 different products, one with an R configuration about the anomeric carbon and the other with the S configuration. So that last hydroxyl group can actually be in 2 different positions. On one hand, the hydroxyl group would be cis to the last carbon in the equatorial position. So it'd be cis to this last carbon over here, and it's in the equatorial position. And we call this the beta anomer. Then on the other hand, I guess, it could be trans to that last carbon group, which would place it in the axial position down here. So I guess it could be down here in the axial position, and we call it the alpha anomer when the hydroxyl group is in the axial. And I kind of remember that a little bit easier. Alpha for the axial position of that substituent. And I guess I've also heard that fishies are down in the sea and birds are up in the air. So if that helps you keep them straight, you might be able to use that also. Now you've got to remember that what caused this ring to close in the first place was some amount of acid or base. And the amount of acid and base in water is actually kind of capable of doing that, because that's what facilitated this ring closing process in the first place. And in water, the ring can actually open and close spontaneously. And when it opens up, the C1 and C2 bond right here can actually rotate. And when it closes again, you can form either the alpha or the beta product. So this thing is constantly opening and closing to form the 2 different products. And we call that process where it opens and rotates and closes again mutarotation. So this thing is mutarotating in the water at all times. So mutarotation. And the outcome is that we end up with both configurations, the beta and the alpha, in the equilibrium concentration. So for glucose, that's going to be about 36% alpha and about 64% beta. And the reason that the alpha configuration is less favored in equilibrium for glucose is because the transpositioning of the hydroxyl group creates some steric hindrance. But this is pretty individualized for different sugars. So I guess the most general rule, I suppose, that you could apply to all cyclic sugars would be to say that the beta anomer, that the beta anomer, it is the one with the anomeric oxygen in the cis position with respect to the last carbon. All right, so in a previous video, I talked about how cyclic monosaccharides like this green cyclic glucose can react with alcohols like this pink alcohol to form acetals and ketols. And I believe that I mentioned that sometimes the alcohol that comes in and is reduced is actually another carbohydrate. So let me kind of draw this in here. And it makes sense because what you see with carbohydrates is that they're chock full of hydroxyl groups. They're chock full of these OH groups. And so really they can function really similarly to alcohols in reactions. And when this happens, individual monosaccharides are linked together to make an acetal. And we call this linkage a glycosidic linkage. So this is a glycosidic linkage. linkage. Now, when two monosaccharides are linked together in this fashion by glycosidic linkages, we call the product a disaccharide. A disaccharide. We have di, which means two, and saccharide, which means sugar. So sugar. So two monosaccharides linked together, they're called a disaccharide. Now, with disaccharides, most commonly the glycosidic linkage forms between the anomeric carbon, or C1. So remember, this is the anomeric carbon, that's C1. So over in our glycoside here, be right here, just the same. We've got C1 of the first sugar, and then C4 of the second sugar. So right here would be C4, and it's just the same over here. So right here we have C4, and that's the second sugar. So we call this a 1,4 glycosidic linkage. And then just like we could further break down our monosaccharides into alpha and beta based off the orientation of the anomeric hydroxyl group, we can more specifically call the 1,4 linkage an alpha or a beta linkage. Again, based off what is now the orientation of the OR group on the anomeric carbon. So same rules apply. If the group is cis with respect to the sixth carbon, it's beta, and of course, if it's trans, it would be an alpha linkage. So in this case, our OR group, right now with disaccharides, most commonly the glycosidic linkage forms between the anomeric carbon, or C1. So remember, this is the anomeric carbon, that's C1. So over in our glycoside here, be right here, just the same. We've got C1 of the first sugar, and then C4 of the second sugar. So right here would be C4, and it's just the same over here. So right here we have C4, and that's the second sugar. So we call this a 1,4 glycosidic linkage. And then just like we could further break down our monosaccharides into alpha and beta based off the orientation of the anomeric hydroxyl group, we can more specifically call the 1,4 linkage an alpha or a beta linkage. Again, based off what is now the orientation of the OR group on the anomeric carbon. So same rules apply. If the group is cis with respect to the sixth carbon, it's beta, and of course, if it's trans, it would be an alpha linkage. So in this case, our OR group, which the OR group is this whole carbohydrate, is cis with respect to the C6 carbon. So we have a beta 1,4 glycosidic linkage. And if that bit of naming confused you a little bit, I went over that in greater detail in a different video. But what I want to focus on here are some of the common disaccharides. So let me clear some space. Let me give us some room. I'm going to go ahead and fade in a drawing that I did a little bit ago to save just a bit of time. And what we have here is a disaccharide. You see two carbohydrates, two monosaccharides linked together. And this one happens to be lactose, which you might be familiar with. So lactose. And lactose happens to be really the principal disaccharide found in milk. And that's actually true for both human milk and for cow milk. And unlike really most disaccharides, lactose isn't really appreciably sweet. It consists of one galactose, so this one right here is galactose, and then one glucose carbohydrate, and they're bound together by a 1,4 glycoside bond, just like we saw before. So we've got the 1 and the 4, and this is a glycoside bond, and this one happens to be in the beta orientation. So lactose is a disaccharide made of galactose and glucose joined together by a beta 1,4 glycoside bond. Now next up we have maltose. So let me write that in here. We've got maltose, and maltose is again a disaccharide, but this time it's made of two individual glucose units. So we've got a glucose right here, and we've got a glucose right here, and they're bound together similarly by a 1,4 glycoside. So we've got the 1 carbon right here, that's this one, and we've got the 4 carbon over here. So this is again a 1,4 glycosidic linkage, but as opposed to lactose up here, this one's actually alpha. You can see that this OR group, the second carbohydrate, which is functioning as the OR group, is in the trans position with respect to the first carbohydrate's 6 carbon over here. So this is an alpha 1,4 glycosidic linkage, and it binds together 2 glucose units. So that's maltose, another pretty common disaccharide. And then last but not least, let me pull in here for you sucrose. And sucrose is actually probably the most common disaccharide in all of nature, and you deal with it quite frequently, I'd imagine, because sucrose is the principal disaccharide of table sugar, which comes from sugarcane. So sucrose is actually quite sweet, but it's different, substantially so, from maltose and lactose. And I want to point out a couple of the key differences. So in lactose and maltose, both of these up here, you have 2 pyranoses. Remember, pyranoses are 6-membered carbohydrate rings. I went over that in a previous video, but we have 2 6-membered rings bound together by this glycoside. And in sucrose, that's different. We've got a 6-membered glucose right here. This is glucose bound to a 5-membered or a furanose fructose. So we've got fructose right here. So fructose. And what happens is you have both of the carbohydrates linked together by their anomeric carbons. So right here, we've got 2 anomeric carbons linked together. Now that's different than maltose and lactose. So for example, right here is the anomeric carbon of both maltose and lactose. It's over here. That's the C4 that's bound. So these are both linked together by their anomeric carbons. And what happens is you have 2 acetals that are formed. So we've got an acetal right there. And remember, an acetal is when a carbon is linked to an OR group over here and an OR group over here. And then you have a second acetal at the fructose's anomeric carbon. And so with maltose and the same thing with lactose, you have a hemiacetals that are formed. So you've got an acetal right here, and then you've got a hemiacetal over kind of on the tail on the second glucose. That's a hemiacetal, and you can look up, and it's the exact same thing for lactose. But what happens here is, remember that with a hemiacetal, you can add on a second OH group to form another acetal. A hemiacetal can be further reduced into an acetal, but once you have an acetal, you can't further reduce it. So that makes sucrose a non-reducing sugar, and then lactose and maltose are both reducing sugars. And so lactose, maltose, and sucrose are probably the 3 most common disaccharides, and they give us a good basis for disaccharides. And then really polysaccharides are just an extension of this thought. So let me clear some space. And for those reducing sugars like maltose and lactose that are left with a hemiacetal group at the end, we can keep adding sugar groups onto the chain. That's kind of this reducing characteristic. They can keep growing, which ends up making more acetal groups, but always leaving a hemiacetal group on the end. So I've kind of pre-drawn in another drawing here. Let me make a little bit more room for it. And that's what I've shown here. I've shown just kind of the addition, a couple additions of extra carbohydrates onto disaccharides. So both of these have 3 carbohydrates, and you could keep going, but that's what makes them polysaccharides. So this first one that I drew in is a polysaccharide called cellulose. And cellulose is found in the cell walls of really nearly all plants, and it gives support and structure to wood and to plant stems. And really cotton is essentially just pure cellulose. But cellulose is a polysaccharide made of repeating glucose units that are joined together by beta 1,4 glycosidic bonds. So all of these are beta 1,4 glycosidic linkages. And really it forms an unbranched, just kind of straight chain, and that's the polysaccharide cellulose. Now down here I have another polysaccharide, which is also super common, and this is starch. And you can see that really this is made up of repeating glucose units here. The difference is that these linkages are alpha, still 1,4. So still 1,4 linkages, but these are alpha units. And really the functional difference here is that as humans, we have the enzyme to break down these alpha 1,4 linkages, and we can use starch, which again is found in a lot of plant products, as a source of energy, because we can break these down into glucose to undergo cellular respiration, but we lack the enzyme to break down the beta 1,4 glycosidic linkages of glucose, so we can't appreciably use cellulose as an energy source. And then one last polysaccharide that I want to show you is really very similar to starch. So I'm going to use the starch as a little basis here. But if you kind of branch off of the starch every once in a while on the C6 carbon, so that's the C6 carbon right here, and you add on another glucose. So I'll stop there. This is another glucose. You can keep going with alpha 1,4 linkages again, and you can form essentially just branches. So this one would go here, and then you could maybe down the line here have another one. And so these are mostly alpha 1,4 linkages. Every once in a while you get an alpha 1,6 linkage thrown in there, which creates some significant branching. And so if it's highly branched, we call it glycogen. And that's a little bit dumbed down of a concept, but essentially that's what glycogen is. It's a major polysaccharide made of alpha 1,4 linkages with that are heavily branched by these alpha 1,6 breaks. But glycogen, its significance for us is principally as a source of storage of energy. So we can build glycogen stores in our body, and it creates a really functional store of glucose, because with all these branches, we have a lot of tails of glucose that can be chopped off pretty quickly to get a fast glucose source. So that's probably a good start for polysaccharides as well. We've got cellulose, which is beta-1,4 linkages of glucose in a straight chain. We've got starch, which is essentially kind of a chain of alpha-1,4 linkages of glucose, and then we've got glycogen, which is really similar to starch, except that there are alpha-1,6 linkage breaks in here that enable us to form kind of chains of this polysaccharide.
Start with an aldehyde or ketone and add a catalytic amount of acid or base. You'll find the aldehyde or ketone is going to be in equilibrium with this. You start with an aldehyde or a ketone and add a catalytic amount of acid or base. You'll find the aldehyde or ketone is going to be in equilibrium with this product over here on the right, which we call an enol. So the name enol comes from the fact that we have a double bond in the molecule, so that's where the ene part comes in. And we also have an alcohol, right? You can see the OH over here, so that's where the OL comes in. So this is the enol form. And then over here, this is the keto form. So the keto form and the enol form. And these are different molecules. They're isomers of each other. So we call them tautomers. And they're in equilibrium with each other. They're not different resonance structures. Let's see if we can analyze our aldehyde or ketone to see how to form our enol. And so if we look at the carbon that's next to the carbonyl carbon, we call this the alpha carbon. And there are two hydrogens attached to the alpha carbon in this case. Let me go ahead and draw those in. And those are called the alpha protons. And so if we think about transferring one of those alpha protons from the alpha carbon to the oxygen, right, even though it's most likely not the same proton, just helps to think about doing that. We can also think about moving the double bond, right? So over here on the left, the double bond is between the carbon and the oxygen, and we're moving that double bond over here between the two carbons. So transferring one alpha proton and shifting your double bond converts the keto form into the enol form. And then we also have a hydrogen, right? So over here, right, we still have a hydrogen left on this carbon. So let me go ahead and draw in that hydrogen. So that's this hydrogen in blue here. So that's how to think about converting a keto tautomer into an enol one. Let's look at the acid catalyzed mechanism for this. So if we start with our aldehyde or ketone and add H3O+, right, the first thing that's going to happen is protonation of our carbonyl. And so lone pair of electrons picks up this proton like that. So we can go ahead and draw that. We would protonate our carbonyl. So now our oxygen would have a +1 formal charge. Let me just go ahead and draw in those electrons here. And let's say we started with an aldehyde. So we'll make this an H. So the lone pair of electrons on our oxygen, right, picked up a proton like that. We can draw a resonance structure for this, right? We can move these electrons off onto our oxygen. So let's go ahead and show a resonance structure. So we have our R group, right? And now we would have our oxygen with two lone pairs of electrons. Let me go ahead and draw in those two lone pairs of electrons on our oxygen. And then we took a bond away from carbon, right? So we took a bond away from this carbon. So this carbon right here, so +1 formal charge on that carbon. And then we could show the movement of those electrons. So these electrons right here, I'm saying moving out onto the oxygen like that. And so this is our intermediate here. All right, so we know that our alpha carbon has two protons on it. So once again, let's find our alpha carbon. Here it is right here. And we know we have two protons attached to it, two alpha protons, if you will. And so in the next step of our mechanism, we're going to get a molecule of water acting as a base. Let me go ahead and show a molecule of water here. And the water is going to take one of those alpha protons, right? Let's say, once again, it takes this alpha proton and leave these electrons behind. They're going to move in here to form our double bond. So let's go ahead and draw our product, right? So we would have our R group here. And now we would have a double bond formed between our two carbons, and then we would have our oxygen, and then we would have two lone pairs of electrons on our oxygen. We would have our hydrogen, and then we would have another hydrogen right here. So let's go ahead and follow some of those electrons. right? So let's go ahead and make these electrons in here blue, right? So these electrons are going to move in here. It doesn't really matter which one you say it is. Let's just say it's that one, right, to form our double bond. And then the electrons in red moved off onto this oxygen. And then we said that these electrons were in magenta. And so you can see that we have formed our enol here, right? So this is our enol, right? And then we started with our keto form like that. So keto-enol tautomerization. Let's look at the base catalyzed version, right? So once again, we start with our aldehyde or ketone. But this time we're going to add a base, so something like hydroxide. And so we find our alpha carbon. So here's our alpha carbon, once again with 2 alpha protons. So we go ahead and draw in those 2 protons here. And the base is going to take one of those protons. Let's say it takes this one over here on the right. That leaves these electrons behind on this carbon. So let's go ahead and draw the resulting anion here. So we would have our carbonyl like that. Right, and once again, let's say we started with an aldehyde, and then we would have a lone pair of electrons on this carbon, the carbon in red here. So let me go ahead and identify those electrons. So these electrons in here in magenta have moved off onto this carbon like that, which gives that carbon a -1 formal charge, right? It's a carb anion. There's still a hydrogen attached to that carbon in red, right? This hydrogen right here is still attached to it. I'm just not drawing it in so we can see a little bit better. All right, so this is one form of the anion that we could have. We could draw a resonance structure to show the other form. So if we move these electrons in magenta into here and push these electrons off onto the oxygen, let's draw the resonance structure. So we would have, right, our R group here, we would have a double bond, and then our oxygen would have 3 lone pairs of electrons, giving it a -1 formal charge. And then we would have our hydrogen over here. So the electrons in magenta, right, moved in here to form our pi bond. And then we can say that these electrons in here, right, moved off onto our oxygen. So we could go ahead and show that. So let me just go ahead and put the other bracket on here. And so we have 2 forms of this anion. This is called the enolate anion. So this is the enolate anion. This is going to be extremely important in future reactions. And you can see the enolate anion has 2 resonance structures. One where we've shown the negative charge on the carbon, right? So that would be this one right over here. So the negative charge in the carbons. This is our carb anion form. So carb anion. And then we also have a resonance structure where the negative charge is on the oxygen. So we call this the oxy anion. And if you think about which one contributes more to the overall hybrid, oxygen is more electronegative than carbon. And so it's better able to have a -1 formal charge on it. So the oxy anion contributes more to the resonance hybrid. All right, let's think about the last step in our mechanism, right, to form our enol. If we think about our oxy anion, all we would have to do is protonate that oxygen here. So we could just go ahead and draw a water molecule, right? So we have a water molecule. This time water is going to function as an acid. It's going to donate a proton. So let's say these electrons in blue, right, take this proton, leave these electrons behind. And so from our oxy anion, we can go ahead and draw our enol product. So we have our R group here, we would have our double bond, we would have our oxygen, right, now protonated like this to form our enol product. So let me just go ahead and show those electrons in blue, right? Picked up a proton here to form our enol. So that's how to get there using base catalyzed. And once again, we will talk much more about the enolate anion in future videos here. So let's look at a situation where the alpha carbon is a chiral center. Okay, so let's look at this right here. So here's our alpha carbon, right? And it's a chiral, let's just say it's a chiral center. So if R and R double prime are different from each other, we would have 4 different things attached to this carbon, right? And so the alpha carbon here is sp3 hybridized with tetrahedral geometry. So let's say it's either the R or the S enantiomer, so it doesn't really matter which one. But you can see now we have only one alpha proton, right? Only one alpha proton. But because there is an alpha proton, right, we can form an enol. So in either an acid or base catalyzed mechanism, right, we could think about the proton here in red. You can think about transferring one to this oxygen and moving your double bond, and then we form our enol, right? So here is our enol. Now let's look and see what happened to the carbon in red right here. So on the left, right, the alpha carbon was sp3 hybridized with tetrahedral geometry. Now this carbon is sp2 hybridized with trigonal planar geometry. And so whatever stereochemical information we had over here on the left, right, whether it was the R or the S enantiomer, it's been lost now that we formed the enol. The enol is achiral, it's flat, it's planar. And so when we reform the keto form, right, so one of the possibilities is to form the enantiomer that we started with, but the other possibility is to form the other enantiomer. And so you can see that's what I've shown here. I've shown the hydrogen now going away from us and our R double prime group coming out at us. So this is the enantiomer. And so because we form the enol, right, we can get a mixture of enantiomers. So enolization can lead to racemization. We can get a mixture of enantiomers, and if we wait long enough, right, we can get an equal mixture of these guys. So this one and this one, right, would be in equilibrium with our enol form. And so that's something to think about if you have a chiral center at your alpha carbon. Let's look at two quick examples of keto and enol forms. And so over here on the left, we have cyclohexanone. And on the right would be the enol version of it, right? So you can think about one of these as being this would be your alpha carbon, right? And you can move these electrons in here and push those electrons off, and you can see how that would give you this enol form. So it turns out that the keto form is favored, right? So the equilibrium is actually far to the left, favoring formation of the keto form. So even under just normal conditions, so not acid or base catalyzed. And so there's only a trace amount of the enol present. However, there are some cases where the enol is extra stabilized, and that's the case for this example down here. So we have the keto form, and we have the enol form. So once again, you can think about these electrons moving in here, pushing those electrons off, giving you your enol form. And this is a specially stabilized enol, right? So this is phenol right here. And we know that phenol has an aromatic ring. And so the formation of the enol form is extra stabilized because of this aromatic ring. And so this time the equilibrium is actually to the right, and much more of it is in the enol form than the keto form. So in this case, we have some special stabilization.
Right. Right. You got the brand method videos. Brand method videos. Brand method. Brand method videos. Which was that one? Oh. Okay. Gotcha. Okay. Yeah. Cool. Thank you. Thanks, Yusuf. Oh, thanks, Yusuf. Thank you, Yusuf. All right. I need to pee. We'll finish up here, and then I need to review chemistry. Let's put this away and then come back. see. Yep. Yeah, let me just see. Yup. Yup. Let's read this book. Yeah. Let's read that book. Maybe. Maybe. Yeah. Hello. Hi. How are you? Very nice to meet you. Very nice to meet you. Hello.
Have you ever realized that at your deepest, most inner core, you're not really you? Well, think about it. The minute you eat something and swallow it and it passes in through your gastrointestinal tract, that's the external environment. That food that you just took in was a part of the outside world. And the tract that it's going to follow in through from your mouth till the point that you expel it in the bathroom is actually not you. That's the external environment. How weird is that? So in this video, we're going to do an overview of the gastrointestinal tract. I'll talk about each of the individual parts and what their main overall functions are. And then in subsequent videos, I'll go through each of these individual parts and give a more detailed explanation of how they do what they do. All right. So starting off, of course, the first place our food is ever going to go to is our mouth, or the oral cavity. The main functions that we have achieved in the mouth include chewing, the morcellation of food. Also very important is hydrolysis. As you might recall from biochemistry, hydrolysis is just the enzymatic digestion or the enzymatic breakdown, where chewing is the physical breakdown, hydrolysis is the enzyme.
Stop. Bring it back now. Bum, bum, bum. Bum, bum, bum. Bum, 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 bum. Choo, 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 choo.
Enzyme-assisted breakdown of food. And so as we break down food, the goal here is to make what's called a bolus, just a sphere of digested food that can then be swallowed and passed on into our next structure.
Okay.
And so after we swallow the food, where do you think it goes? This guy right here,
Esophagus?
and that's the esophagus, the esophagus. And this, I think, is one of the more boring parts of the GI tract, because all we do here is just propel our bolus. We just pass it on down to the next guy. We don't really even do anything to it. Kind of boring. But the next guy is a little more exciting. Now we get to the stomach. A lot of action going on in the stomach. One of my favorite parts of the GI tract. The stomach is responsible for multiple things, including churning, which is a lot like chewing, except that there are sort of more dimensions of contraction affecting the food and breaking it down. We also have hydrolysis going on here, the enzyme-assisted breakdown of food. In addition to that, you can store food in your stomach if it's not time to pass it on to the next component of your GI tract. And the overall goal here is to make what's called chyme. So we take our bolus and we sort of melt it down, per se, into this more fluid type of substance that we can pass on to our intestines. So we're moving on now to our intestines. So starting from about this point right here, we get our duodenum, and then this kind of, circulates around here, and then we end up at this point. Everything in between, I'll draw it way out here. I'm just going to group together for right now as the small intestine. The small intestine. And there are three parts to this, and we'll talk about that in a subsequent video. But the main functions that we achieve here are hydrolysis and also the absorption of nutrients. And notice this is kind of the first part of your GI tract that you're finally taking in some of the breakdown food products and using them for nutrition to make other products in your body. Great. So now that we've gone through the small intestine, what do you think shows up next? So starting from after the small intestine ended, all the way through this line structure right here, we are going to be passing through the large intestine. The large intestine. You guys remember the other name for the large intestine? It starts with a C. You said colon? Absolutely right. So the colon is also one of the more boring parts of the GI tract. It's really all we have going on here is absorption, but not of nutrients per se, more like things like water or ions or vitamin K. Just things like that are absorbed in the large intestine. So not a very high yield place for acquiring nutrients. And then after that, we're going to pass food on to this structure here. And this is called the rectum. The rectum. Kind of like the stomach of the GI tract. The rectum serves for storage. We hold on to our processed food, if we can call it that anymore at this point, and it's held there until we deem it an appropriate time to expel the food. And so when it's time to expel the food, it'll come out through the anus, through expulsion. And so those are all the key components of our gastrointestinal tract. There are some other accessory organs that are involved here in digestion. I'll have videos to talk about them as well. Those include things like the liver, the gallbladder, the pancreas, and those will come up in subsequent videos.
Thank you, buddy. Appreciate you. Heck yeah. Look at all these. Look at all these. Gotta hit them.
So the first place our food goes for digestion in the body is, of course, the mouth. And the mouth actually has a couple of names, believe it or not. Of course, we call it the mouth most commonly, but it's also known as the oral cavity or even the buccal cavity, the oral or the buccal cavity. And so let's learn a little more about what's going on in the mouth and take a better look right here. The overall goal...
I want to get some yogurt. I should have gone earlier. My bad.
Of the mouth is to take food and convert it into something called a bolus. And a bolus is just a sphere of food that is easier for us to digest. And now we do this in two main steps. So the first thing we do is we chew our food, and this is something we're very familiar with. There's a very fancy scientific term for chewing, and that's called to masticate or mastication. That's just to chew your food. And there are two things in our mouth that allow us to chew. First, of course, are our teeth, and we'll talk about these extensively in another video. And the second is our tongue. The tongue, as you know, sits right here, and it has a fancy name as well, which would be important to know. It's called the lingula, and that will come in handy in a little bit. The tongue is made up of two types of muscles. There are extrinsic muscles that sit outside of the tongue and anchor into the tongue, and there are also intrinsic muscles. And intrinsic muscles are those that only sit within the body of the tongue. They're only located in here. Extrinsic muscles let us do things like elevate or raise the tip of our tongue, and the opposite, depress or lower the tip of our tongue. It lets us protrude our tongue out of our mouth, and it also allows us to retract our tongue back into the mouth. On the other hand, intrinsic muscles, because they're only located within the body of the tongue, will change the size of the tongue as it contracts. So there are types of muscles that can shorten and widen your tongue, and these are ones that run from the tip of the tongue to the back of your mouth. And so we'll say they run anterior, A, to posterior. And then there are also muscles in your tongue that can allow it to lengthen. And narrow. So narrow because we're pulling the tongue out, and these are ones that run from your right side to the left side of your mouth, or side to side. So right to left over here. All right, awesome. So after we've accomplished mastication, what's the next step? Well, the next step is that we break down the food particles by hydrolysis. And hydrolysis, as you might recall, is a process where enzymes break down macromolecules. Now, the enzymes that cause hydrolysis in our mouth come from glands. And there are a bunch of glands that sit in our mouth, and we'll talk about which ones. They each contribute a certain component of our saliva that we'll talk about right here, and they do different things. So one, our glands can primarily release serous content. So serous content means things that are rich in enzymes and salts. All right, so we'll focus on enzymes. The other type of content our glands can release are mucinous things. So mucinous things, which are mainly composed of mucin, which you might recall is sort of the same way we spell mucus. And the whole point of mucin is to wet the food to make it easier to wrap up into a bolus and send to the back of our mouth to swallow. Enzymes, on the other hand, and I'll clarify this right here, will cut the food. We'll break it down by hydrolysis. So the first gland I'll mention is the largest gland that we have. They're called the parotid glands, and they sit on the side of your mouth right above the jawbone, and these release about 25% of what's in saliva. And because they're green, they're mainly serous, so they contain enzymes, and we'll talk about which enzymes in a second. The next type of gland that we have, it's kind of a mouthful, these are submandibular glands. And these guys release about 70% of saliva, and they sit, as the name suggests, below the mandible, which is the jawbone. And these are also mainly serous, but they certainly have some mucinous stuff that they release as well. So the next gland that we have is called the sublingual gland. And just like the name suggests, this guy sits right below our tongue, or our lingula, as we just learned that term, and it makes up about 5% of our saliva. And as the color suggests, it mainly releases mucin. It does release some enzyme, but less so than the mucinous stuff. And then finally, the last gland that we have that contributes to hydrolysis in our mouth is called von Ebner's gland. So von Ebner's gland, which releases less than 5% of our salivary content. It's very little. And these guys are mainly located at the tip of our tongue. And what's special about von Ebner's gland is that they release an enzyme called lingual lipase. Lingual lipase, which, as the name suggests, break down lipids, or more specifically, triglycerides. And these triglycerides are broken down into free fatty acids, as well as diglycerides or monoglycerides. So I'll just write DG and MG for diglyceride and monoglyceride. And so that's what von Ebner's does, and that's why that's unique. The other three all release, to some extent, an enzyme that's called alpha amylase. Alpha amylase, which is an enzyme that will take carbohydrates like starch, which is just a big stack or chunk of carbohydrates, and break it down into smaller carbs. I'll just write smaller carbs here. So it'll break starch down into smaller carbs to help with digestion. And when I say digestion, I should clarify that the amount of hydrolysis, or the extent of breakdown that we have from these enzymes here, and also from the cutting of food, is very insufficient for absorption of nutrients. The only reason that we actually have digestion occur by enzymes in the mouth is for taste. When we break down our starch and when we break down our lipids, that helps us really appreciate some of the fats in our burgers or some of the sugar that's in our sodas. The problem, though, is when we have too much sugar in our mouth, because the mouth likes to sit around at a pH of about 7, pretty neutral. But when we have a lot of sugar, as you know, there are a bunch of hydroxyl groups that sit on your glucose molecules. Hydroxyl groups can be acidic. And if we drop the pH down to something like less than for absorption of nutrients, we'll take carbohydrates like starch, which is just a big stack or chunk of carbohydrates, and break it down into smaller carbs. I'll just write smaller carbs here. So it'll break starch down into smaller carbs to help with digestion. And when I say digestion, I should clarify that the amount of hydrolysis, or the extent of breakdown that we have from these enzymes here, and also from the cutting of food, is very insufficient for absorption of nutrients. The only reason that we actually have digestion occur by enzymes in the mouth is for taste. When we break down our starch and when we break down our lipids, that helps us really appreciate some of the fats in our burgers or some of the sugar that's in our sodas. The problem, though, is when we have too much sugar in our mouth, because the mouth likes to sit around at a pH of about 7, pretty neutral. But when we have a lot of sugar, as you know, there are a bunch of hydroxyl groups that sit on your glucose molecules. Hydroxyl groups can be acidic. And if we drop the pH down to something like less than pH of 5.5, we can actually start to demineralize or break down teeth because of the acidic nature of your mouth. And so I'm going to keep that in mind next time I reach for a soda.
Okay.
After the food is
Hold on,
swallowed,
guys. Let me watch my answer quick. We'll finish this though. Maybe I can try to see if I can finish this one in hormonal regulation. Oh yeah, especially hormonal regulation.
fluid leaves the mouth and then goes next to the esophagus. So let's focus on that. And just to make sure we all know kind of how far the esophagus goes, so I'm going to draw in some lines right here to show where it starts up here and then it ends right about there. And kind of where I've drawn the lines as well, there are sphincters that sit to make sure food only flows in one way. Up here we have the upper esophageal sphincter. And so just to reiterate, a sphincter is just a circular localization of muscle. So just a bunch of muscle that sits in a ring right here that makes sure that it's closed unless we tell that muscle to relax so we can pass food along. And so when I say that we're going to tell the muscle to relax, that implies then that this muscle here is under our control. So it's composed primarily of skeletal muscle. So it's under voluntary control. And down here, I'll draw a squiggly line, we have the lower esophageal sphincter. So this is a little tricky because we call it a sphincter. You know, it smells like a sphincter, looks like a sphincter, but it doesn't actually work like a sphincter. So it's sort of, I guess, a scientific joke, if you'd like to call it that. Because we don't have a ring of muscle that sits here that opens and closes whenever our body deems it's an appropriate time to. What do we have instead? Well, we actually have a sheet that kind of sits right here. There's a sheet of muscle that lines the connection between the thoracic cavity and the abdominal cavity. So you can imagine that you have a thoracic cavity above. Things that would sit here would be your lungs and your heart. And then below, and I'll draw that right here, you have an abdominal cavity. So the abdominal cavity that's going to have most of the GI tract. And this muscle that we have that sits here, that's going to be the diaphragm. You've probably heard of this. This is voluntary skeletal muscle that contracts to pull downwards to help us breathe. When it moves downward, the lungs inflate there. So the diaphragm sits here and it actually makes a ring around this lower esophageal sphincter. And the diaphragm is actually the lower esophageal sphincter because it just sits there holding the esophagus in place. And that's why over time, we can have what's called a hiatal hernia. The esophagus can move upward and downward through this lower esophageal sphincter, and we'll have gastric acid from the stomach reflux upwards and give us heartburn or gastroesophageal reflux disease, GERD. So that's why we have heartburn, but rodents or horses don't. Rodents and horses actually have their own true sphincter that sit here. So instead, they have an actual dedicated ring of muscle rather than a sheet. Now, the other thing about the esophagus, which is pretty interesting, is that it works as a passageway for food. It doesn't do much. The only process that it can kind of claim to have any stake in is what's referred to as peristalsis. And this is going to be an important term for the discussion of the rest of the GI tract. Peristalsis is just the wave-like propulsion of food. Wave-like propulsion. I'll just write that for now. Because you'll have the contraction of the esophagus at one point up here, like so, and by doing that, it relaxes down here. It relaxes here. Discussion of the rest of the GI tract. Peristalsis is just the wave-like propulsion of food. Wave-like propulsion. I'll just write that for now. Because you'll have the contraction of the esophagus at one point up here, like so, and by doing that, it relaxes down here. It relaxes here. And so when it relaxes here and contracts up here, that means that if you have a bolus of food, like a little circle that's right there, it's more inclined to move this way, directly ahead. And that's peristalsis. And the way we control that is kind of in three parts along the esophagus, because the esophagus is not just skeletal muscle all the way, or not even just smooth muscle. It's split up into thirds. So I'll draw three parts of the esophagus here. So the first part that we have is actually just skeletal muscle. So it's under our voluntary control, skeletal muscle. And so that's 1/3, I'll say the top 1/3 of the esophagus. In the middle right here, we actually have a mix. We have skeletal under our control plus smooth muscle. they kind of work together. So it's sort of in our control, but also not really. So that's going to be the middle 1/3 of the esophagus, the middle 1/3. And kind of as the progression goes, finally, when we get to the end right here, this last 1/3 of the esophagus is going to be smooth muscle. So that's our last 1/3. And so that's how the esophagus is split up into 3 parts. Skeletal at the top 1/3, skeletal and smooth for the middle 1/3, and then smooth entirely for the last 1/3. That's how our esophagus works as well.
Okay. Cool.
Did you know that the human stomach can store up to 4 liters of food at any time? That's about as much as 2 Coke bottles. Insane. So in this video, we're going to see how our stomach helps us process food it just received from the oral cavity and the esophagus. So why don't we take a look here, and I'll zoom in on it so that we can talk exclusively about what this guy is up to. The stomach is primarily 3 steps. First of all, it's going to receive a bolus of food from the esophagus above. This bolus is just food that's been turned into a sphere that can now be processed. Then the stomach can do 2 things here to help process the food even more. The first thing the stomach does is that it churns this bolus, or it churns the food. The muscular walls of the stomach here allow it to compress down and break up this food even more. In addition, there's also a certain degree of hydrolysis, or enzyme-assisted degradation or breakdown of this bolus. And we'll talk about the enzyme that's responsible for this process in a moment. And then finally, after we do all these things, we receive a product that's called chyme. Chyme is just a mixture of whatever the bolus has been broken up to, including the gastric enzymes and juices that we've used. And then the food is going to actually just stay here for a little bit, because the stomach also stores food. It'll store the food until it's an appropriate time for the chyme to be squirted into the duodenum, or the first part of the small intestine, to be processed. And that's why we can store up to 2 to 4 liters of food at any given time. Now, what about the anatomy of the stomach here? How do we release these enzymes and break down this bolus? Let's take a look at a little bit of gastric anatomy right about there and see how it's responsible for the breakdown of food here. We can imagine that the stomach is lined with all these infoldings of the gastric wall that help to increase the surface area. And in doing so, there's actually a layer of cells that sit around here. This layer of cells actually secretes a lot of the components of the gastric juice we're going to see. And it's nicely ripe with a ton of important components. And the main thing to remember in the stomach is that there are 3 types of cells that are involved here. The first type I'm going to talk about are called parietal cells. Parietal cells. And the main thing that's released from parietal cells is hydrochloric acid. Hydrochloric acid, it's a very acidic or a very corrosive acid that's actually more acidic than battery acid. In addition to parietal cells, we also have chief cells. Chief cells. These guys secrete an enzyme called pepsinogen. Pepsinogen. And this is the inactive form of the enzyme. Pepsinogen is not active. In fact, in order for hydrolysis to occur, we secrete an enzyme called chief cells. Chief cells. These guys secrete an enzyme called pepsinogen. Pepsinogen. And this is the inactive form of the enzyme. Pepsinogen is not active. In fact, in order for hydrolysis to occur, we need an enzyme that's called pepsin. How is pepsin made? Well, we're going to this to occur. And this is the inactive form of the enzyme. Pepsinogen is not active. In fact, in order for hydrolysis to occur, we need an enzyme that's called pepsin. How is pepsin made? Well, we're going to need pepsinogen to make it. But the pepsinogen, and whenever you see gin, G-E-N at the end of a name, that means that it's almost there. It just needs to be processed. In order to turn pepsinogen into pepsin, we need hydrochloric acid, which will break down this protein to turn it into this active form that can then be used for hydrolysis. Now, Now, what would happen if we just had a bunch of pepsin or a bunch of hydrochloric acid present in the stomach all the time? What do you think would happen to the stomach? It would probably eat itself alive. Isn't that right? I mean, you've got your cell membrane that definitely has a considerable amount of protein that should be present there. And in addition, you've got this really corrosive acidic substance that can eat through your stomach. And that's actually how you have gastric ulcers. But not all of us have gastric ulcers. What do we also have in our gastric pits right here that help us prevent gastric ulcers from occurring in the first place? Well, the third type of cell that we have sitting in here are actually called mucus cells. Mucus cells. And just like the name suggests, mucus cells release what's called mucin. And this is a coating that will sit around the stomach to make sure that things like pepsin or hydrochloric acid don't degrade the stomach. Without mucus cells, we would eat ourselves alive. So as a review, the three things the stomach will do for us is that it'll churn with its very muscular walls to help break down the bolus in a very physical activity. Also, there's an enzymatic or a chemical process that occurs here where we use pepsin to degrade food. Now, pepsin itself only degrades one type of nutrient, and that's protein. This will break peptide bonds, or the bond that connects amino acids to one another, to degrade your protein macromolecules. So that's the only type of nutrient that's broken down in your stomach. Once we hydrolyze a significant amount of the protein, we're going to produce chyme that is stored in the stomach until it's the right time for it to be released into the next part of your GI tract, called the duodenum, the first part of the small intestine. And that's how your stomach works.
Thank you.
Did you know that the stomach flu can make you temporarily lactose intolerant? It's true. So in this video, we'll talk about how that happens and in detail how the small intestine works. So as a review, once you put food into your oral cavity or your mouth, it's chewed up and then sent down the esophagus where it ends up in the stomach, where it's churned and then introduced to acid where it gets broken down into chyme and then delivered into the first part of your small intestine. Now the small intestine has three different parts to it. So let's take a better look.
All right. All right.
So the first part of the small intestine is called the duodenum, the duodenum. This receives the chyme that just got processed in the stomach, and it's the part of the entire GI tract where the most digestion occurs. The most breakdown of food products will happen in the duodenum. All right, so the next part of the small intestine is called the jejunum. I'll just write that right here, the jejunum. And this is the part of the entire GI tract where the most absorption occurs anywhere. So the most absorption of nutrients is going to happen in your jejunum, the jejunum. Then finally, after your food passes through the jejunum, it gets to the last part of the small intestine, and that's called the ileum, I-L-E-U-M. And the ileum, now this doesn't have a superlative like the most digestion or the most absorption, but there's some pretty important things that are absorbed here. Things like vitamin B12, vitamin A, D, E, K. So there are some important things that are absorbed here. So I'm just gonna write important absorption. There are some important things that are absorbed in your ileum. Now, the busiest part of your small intestine is the duodenum because there are a bunch of things that are involved in this digestion process. So there are four key things to keep in mind. First of all, your stomach is going to be delivering a bunch of chyme or processed food into the duodenum. So you're going to be working with all this chyme here. In addition, you're going to have some stomach acid that processes food into chyme that's going to be present in the duodenum. In addition to the stomach, the liver and the gallbladder are also going to be important to deliver bile to your duodenum. So they give bile. And as I'll talk about in a subsequent video, bile is composed of two different things, bile salts and bile pigments. And beyond the liver and the gallbladder, the pancreas also delivers a couple of very important enzymes for digestion here. So I'm just going to write enzymes for now. And in a minute, I'm going to go through and talk about which enzymes are delivered by the pancreas. And then finally, the duodenum itself has what are called brush border enzymes. Brush border enzymes that are very important for activation of certain enzymes and also for digestion of several nutrients that we're going to discuss. So let's talk a little more about this brush border. Now, if I were to make a little drawing of the duodenum right here, remember that first part of our small intestine, I would draw just this little tube connected right there, and then blow up the wall. I want to take a better look at what's going on right there. We would find then that there's a whole bunch of things that just meets the eye. First of all, the wall isn't just a straight line. There's actually a bunch of infoldings that are present on the wall to help increase surface area. Think about it. If we're trying to digest as much as we can here, we need to make sure that there are a lot of projections or a lot of space where we can make contact with the food that's passing by. So if this is the inside of our duodenum and this is the outside, just like how we drew up here, that's in and that's out, you can notice that this wall here has a whole bunch of projections on it. These projections are called villi, V-I-L-L-I, villi, and a single one of them is just called a villus. just a single villus. And these are just a couple of folds or these outpouchings that help increase the surface area of our duodenum. Now, that's not where the story ends. If we take a closer look at one of these villi, then we'd find that there are even more projections sitting on that, even smaller microscopic projections. So for this single villus that had a horizontal line right here for its shape, if I were to draw it out here, you would notice that it's not a straight line, but instead, these also have a bunch of projections that are present on them. And if you were to guess why all these projections are there, I'm sure you would say, to further increase our surface area. That's sort of the name of the game when we're in the small intestine, to increase our surface area. And so these little guys, cutely enough, are called microvilli. Microvilli. And a single one is just called a microvillus. So we've got these villi right here, or the single villus that you can see if you just blow up the wall of the duodenum. And then if you blow up a single villus, you'll find that they have a whole bunch of microvilli that are found on them too, to increase our surface area, because that allows for better digestion. And when we say brush border enzymes, these are a whole bunch of enzymes that are present on this brush border. Because think about it, these villi and these microvilli, they're no different from bristles on a comb. They act to increase surface area or places where you're going to have interaction with food that you want to digest. And so there are enzymes that are present on this brush border. So just to make the point, all of these microvilli and villi together, that's what makes up the brush border of our duodenum. The brush border, which is the increased surface area of the wall, helps to digest food with our brush border enzymes that are present. And as we'll see later, in the jejunum, it helps for absorption. So now let's talk about the digestion process in detail.
Cool. Let's do it.
So the best way to talk about the digestion process in the duodenum is to talk about the 4 major macromolecules that make up everything in our body, starting off with protein. Proteins are just chains of amino acids. So there's one amino acid, and here's another amino acid, and they're connected by something called a peptide bond. After proteins, we also have things that are called carbohydrates. Carbohydrates, or our carbs, and these are just repeating units of simple sugars attached to each other. You name one simple sugar? Yeah, I think you said glucose. And so something like glucose attached to, say, galactose would be a disaccharide. And this particular disaccharide would be called lactose. So a single sugar would be considered a monosaccharide. 2 of them, a disaccharide, and then a whole bunch would be a polysaccharide. In addition to our carbs, we also have nucleotides, and these guys make up our nucleic acid, our DNA, and they're composed of 3 major parts. There's a phosphate group that sits on a ribose sugar that I'm drawing here, this little pentagon, and then right here, you're gonna have a base that's present. And this base is the coding part of your DNA, like adenine or guanine, if you've heard those names before. And then finally, we also have fat. Fat has 2 parts to it. It's got this triglycerol head that has these 3 oxygen groups on it, and then each of these oxygens have a fatty acid tail. So there's 1, there's 2, there's 3. So 3 fatty acid tails that are found here. So now that we know what the main macromolecules are, we can talk about what are the main processes that are involved in breaking these guys up so they can be absorbed into our bloodstream. Starting with our proteins, there's going to be brush border enzyme.
This guy's pretty good.
That are present to help break our peptide bonds, or the amino acid bond that's present. And so I'll just write peptidase to be absorbed into our bloodstream. Starting with our proteins, there's going to be brush border enzymes that are present to help break our peptide bonds, or the amino acid bond that's present. And so I'll just write peptidases here. Peptidases, because as you might recall, whenever you name an enzyme that ends in ase, that means that whatever comes before it is what's broken. So a peptide bond is broken by a peptidase. In addition, the pancreas brings along a couple of important enzymes that'll help break up our proteins. First of all, it's got trypsin. The panc comes before it is what's broken. So a peptide bond is broken by a peptidase. In addition, the pancreas brings along a couple of important enzymes that'll help break up our proteins. First of all, it's got trypsinogen that's present, as well as some chymotrypsinogen. But whenever you see gen at the end of an enzyme's name, that means that it's not ready to work yet. That means it still needs one more cut or cleavage before it can start being completely functional. Well, this is where our brush border comes in handy again, because there's an enzyme that's present on the brush border. It's called enteropeptidase. Enteropeptidase, that is specifically present to break down trypsinogen into its active form called trypsin. And the same thing with chymotrypsinogen into chymotrypsin. These guys are going to be able to break down your peptide bond as well, just like peptidases are able to do, but need a little kick or a little cut in order to start working. And once we gobble up our proteins, we'll have our single amino acid cleavage before it can start being completely functional. Well, this is where our brush border comes in handy again, because there's an enzyme that's present on the brush border. It's called enteropeptidase. Enteropeptidase, that is specifically present to break down trypsinogen into its active form called trypsin. And the same thing with chymotrypsinogen into chymotrypsin. These guys are going to be able to break down your peptide bond as well, just like peptidases are able to do, but need a little kick or a little cut in order to start working. And once we gobble up our proteins, we'll have our single amino acid subunits then and be absorbed. When we get to carbs, we've noticed that the pancreas is also pretty helpful here as well, because the pancreas releases an enzyme that's called amylase that can help break up the sugar bond, or this glycosidic bond is another name for this link right here, in certain carbohydrates. When we get to carbs, we've noticed that the pancreas is also pretty helpful here as well, because the pancreas releases an enzyme that's called amylase that can help break up the sugar bond, or this glycosidic bond is another name for this link right here, in certain carbohydrates. The brush border is also helpful here because they have a whole bunch of very specific enzymes that break the glycosidic bond between very specific simple sugars. For instance, the brush border enzyme known as lactase can only be used to break apart lactose, like I've drawn here. Now, the interesting thing about lactose that I should mention is that when you get the stomach flu, you've got a bug that's just sitting in your tummy. It actually can start inflaming the duodenal wall. And by doing so, it can knock off some of the lactase brush border enzymes. And so you won't have lactase. You won't be able to break down lactose. You won't be able to separate our glucose from our galactose. And so temporarily, you're going to be lactose intolerant. Most people gain this ability back, but you can understand now how precious these brush border enzymes are to us. And so they'll help break up certain disaccharides. The pancreas will do its job as well. And eventually you'll just have your simple sugars that are going to be left over here. And remember, the name for each single unit is called a monosaccharide. When it comes to nucleotides, the brush border helps us as well. The specific enzyme set that we have on our brush border that helps break apart nucleotides are called nucleosidases. And the reason why we have nucleosidases and not nucleotidases is because it breaks this bond right there, resulting in this phosphate group sticking on the ribose sugar. But now we've got our base as a completely separate unit from the nucleoside. Finally, when it comes to fat, we're going to get some help from bile, as I mentioned earlier. And bile, if you recall, comes from our liver and our gallbladder. So these guys are going to release some bile into our duodenum. And they're going to help emulsify or organize our fat. So I'll write here in parentheses organize, because they're not really involved in breaking them down. They're there to help organize our fats. One of the main things that help us actually break it down is from the pancreas. The pancreas releases something that's called lipase. And the lipase comes in and cleaves right about there. So that way, each of these single fatty acid chains break off. And so you'll have these 3 fatty acid chains that are hanging out right here, including your triglyceride head. That's going to be a separate unit altogether. So now you've got these 4 things that came off of this one fat molecule. Triglyceride.
Now we're moving. See, now we're moving like this.
Head. That's going to be a separate unit altogether. So now you've got these 4 things. Triglyceride. You'll have these 3 fatty acid chains that are hanging out right here, including your triglyceride head. That's going to be a separate unit altogether. So now you've got these 4 things that came off of this one fat molecule.
Yes, sir.
All right, great. So now we have all of our monomers ready to be absorbed. How does the absorption process work? Let's take a look. So now we're so close. We've got all of our monomers, but we need to figure out how the heck are we going to get them inside of our...
All right, let's take it a minute. I'm still human after all. I can't do everything I want to do. 8. 8. We can try to do this one and another one today. And tomorrow we finish all of them. I'm going to read the whole book. And I have some other videos I want to do. Yep. Yes, sir. I'll be back. Oh. All right, let's get back to it. Yeah, buddy. Water. Let's finish up these two, and let's we'll finish up these two. Wash this real quick. I'll take a quick cold shower afterwards, and then I have to hit the physio class. Yep.
With our amino acids here, these guys are going to be shuttled into cells using what's called primary active transport. Primary active transport. Now, if I say primary here, what does that specifically indicate is used? Now, you might recall when we use active transport, that means we need a little bit of energy to get something to happen. And the form of energy that we use in primary active transport comes from ATP, the energy unit of life, adenosine tri as in 3-phosphate. And so if we look at a single enterocyte or an intestinal cell, there'd be a protein that's here on the cell membrane. This protein would break apart our ATP, cleaving off one of the phosphate groups to release adenosine diphosphate, so that's 2-diphosphate, and in doing so, would allow our amino acid to enter into our enterocyte, or our intestinal cell. From there, the amino acid can undergo a couple of different steps here on the cell membrane. This protein would break apart our ATP, cleaving off one of the phosphate groups to release adenosine diphosphate, so that's 2-diphosphate, and in doing so, would allow our amino acid to enter into our enterocyte, or our intestinal cell. From there, the amino acid can undergo a couple of different steps, but eventually will leave the enterocyte and go to a blood capillary, where it enters the bloodstream and then can be shuttled anywhere else in the body for use. Monosaccharides or sugars sort of have a similar thing going on, but instead of primary active transport, we have what's called secondary active transport going on. So if we use ATP for primary active transport, what do we use for secondary? Well, the fact that we're saying this is still active transport means that there was some energy that was used at some point. And the energy actually was invested in setting up an ion gradient. And so the ion gradient then could be used by allowing something like sodium to flow down its gradient, to go from a place of high concentration to low concentration where it can relax. And by allowing that to occur, energy is then harnessed, allowing a monosaccharide or a sugar to enter into our enterocyte. And just to make sure we're complete, I'm going to draw the protein transporter we have here, as well as one on the other side, and show that there is a sodium ion that's flowing into our enterocyte down its concentration gradient to end up in the enterocyte with the sugar. And sort of the same thing happens on the other side, except as the sugar leaves, sodium on this side is entering. So the sodium is still flowing down its concentration gradient, but it ends up inside the enterocyte while the sugar leaves and goes to the blood capillary. This also ends up in our bloodstream and can go anywhere in the body to be blood capillary. So this also ends up in our bloodstream and sugar leaves and goes to the blood capillary. So this also ends up in our bloodstream and can go anywhere in the body to be used. The nucleoside and the base sort of use the same mechanism that amino acids do. So I'm just going to write primary active transport right here. And you can take a look above to see how that happens. And by doing that, you can imagine where they're going to end up. And that's right, the blood capillary as well. And that takes us to our last macromolecule, fat. Now, the thing about fat that's rather redonkulous is that because it's got this really non-polar tail, if it ever shows up next to an enterocyte like this guy, all it has to do is just diffuse across the membrane, and then it ends up on the inside. In the enterocyte, all of our fatty acids are going to be reorganized into what are called chylomicrons. Chylomicrons. And like the name, chylomicrons themselves are too big to fit directly into a blood capillary. I couldn't even fit it here in this enterocyte. So it doesn't actually directly go into the blood capillary. It is too big to do that, too big to go to the blood capillary. Instead, chylomicrons will be absorbed into what are called lymphatic capillary, also known as a lacteal, a lymphatic capillary. And these are big enough to accommodate our chylomicrons. Here, they're going to be further digested and broken down into smaller bits. And by the time that happens, they'll end up in veins that will send the digested fat through the heart and eventually to arteries that can then distribute them wherever they need to go in the body. And so you can appreciate a lot that's going on here. We've talked about how all 4 of our major macromolecules are digested in the duodenum, the place where the most digestion occurs in the GI tract. And now we just talked about how they're absorbed, most likely in the jejunum, right? Because the jejunum is where the most absorption occurs anywhere in the GI tract. And that
Yes, sir. Sir, yes, sir. Yup. Okay. Excuse me. Yup. Yup, 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 yup. Do you have the ring? Do you have the ring? The ring of Mordor. Do you have the ring? Sir, sir, do you have the ring? What are you talking about? What are you talking about? What are you talking about? Oh no. Oh no. What are you talking about, man? Are you okay? Are you okay? Oh no. Oh no. Oh no. Oh no. Yes, sir. Get on to the liver. We're not done yet.
The next accessory organ we're going to talk about in the GI tract is the liver. The liver. And that's this big fatty guy right here. Now, the liver has to be one of the coolest organs in the body. It's the only one that you can take a piece of, this small chunk right here, and transplant into a recipient that has cirrhosis or liver
Hold on,
failure.
buddy. Hold the phone. Obama phone. Did you know Obama gave me a phone? Obama phone. We might as well. Wait. What sign is on? All right, see what we got here. Where's the patient?
And it can grow to become a much larger organ that can sustain the patient. How wild is that? And so to better understand the liver, the next accessory organ we're going to talk about in the GI tract is the liver. The liver.
No.
And that's this big fat.
That income was pretty cool. Pretty good. I don't think I like red. Maybe. Oh yeah. He's okay.
fatty guy right. The next accessory organ we're going to talk about in the GI tract is the liver. The liver, and that's this big fatty guy right here. Now, the liver has to be one of the coolest organs in the body.
Oh,
It's
yeah?
the only one.
Oh, yeah? Tell me more, buddy. Tell me more, buddy. Oh, yeah? Then tell me more. I want to listen to you more. Drop the knowledge, teach.
One that you can take a piece of, this small chunk right here, and
Go back, buddy.
The next accessory organ we're going to talk about in the GI tract is the liver. The liver, and that's this big fatty guy right here. Now, the liver has to be one of the coolest organs in the body. It's the only one that you can take a piece of, this small chunk right here, and transplant into a recipient that has cirrhosis or liver failure, and it can grow to become a much larger organ that can sustain the patient.
So are you telling me that the liver is regenerative? Isn't that so cool?
How wild is that? And so to better understand the liver, we'll start by discussing the main functions it's responsible for. The first thing we need to think about is that it's responsible for metabolism. And that involves the breakdown of nutrients, or catabolism.
Hold the phone. Hold the phone. Like a little bit.
Responsible for metabolism, and that involves the breakdown of nutrients, or catabolism. I'll just write catch right here, catabolism, as well as the buildup of larger macromolecules, and that's through anabolism.
Anabolism, that's right.
So catabolism and anabolism are achieved in the liver. The other function the liver is responsible for is storage of these nutrients. When we're not breaking them down or building them up, we need to have a place for them to hang out. And so they're responsible for the storage of our carbohydrates. So I'll just write carbs right here, and also mainly our fats. So these two guys. And they're stored in three different ways. First, carbs or fats can be stored as glycogen. Glycogen is just a polysaccharide, so a linkage of a whole bunch of monosaccharides or simple sugars. The other thing that we can store our carbs or our fats as are lipoproteins. Lipo meaning fatty and proteins meaning, well, protein. And then lastly, we can also store these guys as triglycerides, which is one of the forms of fat that we ingest in our food. Now, these are two of the major macromolecules we use for energy. The other major macromolecule class that the liver sees are proteins, but these aren't really stored in the liver. Instead, they're processed into molecules like albumin and then cast off into the bloodstream, where they'll float around and carry out other functions until they need to be retrieved by the liver to be broken down or used for other molecules. The other major process the liver is responsible for is called detoxification. And this is one of those awesome scientific terms where the function is in the name. This is where we take toxins and modify them so they can't harm our body. This is achieved mainly by cytochrome.
So we'd have more likely what in the liver? Anybody in the chat know? Correct. We'd have more smooth endoplasmic reticulum cells in the liver. Correct. You know what you get? You get a omega-3. Well done, sir. Can we get a B12 shot here too? I mean, B12 pill. I'm a B12 shot. Let me get a B12 pill here. Yes, we can. B12 right here for you, sir. Thank you.
P450 enzymes. Cytochrome P450. The function is in the name. This is where we take toxins and modify them so they can't harm our body. This is achieved mainly by cytochrome P450 enzymes. Cytochrome P450. And these are kind of funky enzymes because unlike the other ones you've probably heard about before, these don't bind a specific single substrate or molecule. If you remember an enzyme like phenylalanine hydroxylase, that's something that'll add a hydroxyl group to phenylalanine and only phenylalanine. But cytochrome P bind a specific single substrate or molecule. If you remember an enzyme like phenylalanine hydroxylase, that's something that'll add a hydroxyl group to phenylalanine and only phenylalanine. But cytochrome P450s will take a whole bunch of different substrates and react with them. That's something that's pretty unique to this class of enzymes. Now, because of these cytochrome, that's something that's pretty unique to this, but cytochrome P450s will take a whole bunch of different substrates and react with them. That's something that's pretty unique to this class of enzymes. Now, because of these cytochrome P450 enzymes, we have a problem when we take medications. In fact, we have a decrease in drug efficacy because of this detoxification process. And what we mean by drug efficacy is the amount of an effect a drug is able to have. And so if the liver or these enzymes perceive medications that we ingest to be foreign or like toxins, they're going to try and break them down so they don't cause an effect to our body. So doctors know this. And because of that, a specific dose must be given to account for the amount of a drug that's going to be detoxified by the liver. And finally, as we'll talk about in a separate video in better detail, the last thing that the liver is responsible for is bile production. Bile production. And as you might recall from our discussion on small bowel, bile is needed for the absorption of fats from our food. Okay, so now that we understand what are the main functions of the liver, how does it get all the nutrients that we ingest and absorb from our intestinal tract to be metabolized or stored or detoxified in the liver? Well, let's take a look at the blood supply to the liver. So one of the things that makes the liver so unique is that it has two separate blood supplies. The first that comes in from the intestinal tract is from the portal vein. The portal venous system is another term for it. And the portal vein supplies the liver with nutrient-rich blood. Nutrient-rich. So where do these nutrients come from? Well, food that's absorbed in the intestinal tract will then go through the circulation and end up in the portal vein to be delivered. Venous system is another term for it. And the portal vein supplies the liver with nutrient-rich venous system is another term for it. And the portal vein supplies the liver with nutrient-rich blood. Nutrient-rich. So where do these nutrients come from? Well, food that's absorbed in the intestinal tract will then go through the circulation and end up in the portal vein to be delivered to the liver for metabolism. And so we consider this blood to be nutrient-rich. Where does the liver get its oxygen from? Well, that's a separate blood source. And that's actually through what's called the proper hepatic artery. The proper hepatic artery. And as the name suggests, this is arterial blood that will be supplying oxygen-rich red blood cells. So great. These are the two different sources of blood that go to the liver. Well, what about blood that leaves the liver? There's one main vessel that carries blood out of the liver, and that's called the hepatic vein. The hepatic vein is the exact opposite as the two other types of vessels we just talked about. It's nutrient and oxygen poor. Blood that leaves through the hepatic vein from the liver will circulate back to the heart to receive oxygen, flow past the intestines to receive nutrients, and then return to the liver either through the portal vein or through the proper hepatic artery. The other output of the liver that I guess I should mention right now, we'll talk about in more detail in a separate video, is bile. And bile mainly leaves the liver through what's called the common hepatic duct. The common hepatic duct. Common hepatic duct, that will take bile. The common hepatic duct. Common hepatic duct, that will take bile. So I think we have a pretty good idea of how the liver works. One of the things I kind of touched on when we were talking about our hepatic lobule is that we have bile that's produced in the liver and flows out through the common hepatic duct. Now, bile is composed of two things. One are just bile pigments. Bile pigments are just sort of things that make the color or are not necessarily important for the function of bile. And the other thing that we have are bile salts. Now, this is the most important part. This is what actually helps us emulsify. Remember that term, emulsify, which just means to organize, to eventually absorb our fat. So bile salts help us emulsify fat. They allow us to turn fat into micelles, which can then be absorbed in the ileum. So let's take a step back and get a better idea of how our biliary tree really works. So remember, the liver synthesizes bile, but it does which can then be absorbed as emulsify fat. They allow us to turn fat into micelles, which can then be absorbed in the ileum. So let's take a step back and get a better idea of how our biliary tree really works. So remember, the liver synthesizes bile, but it doesn't necessarily store it. The bile that's made here actually goes through what's called the common hepatic duct. So this is the common hepatic duct that comes out of the liver. So bile that leaves from the liver after it's produced has to go somewhere to be stored. Where is it stored? Well, one of the first places that it's going to go is this duct right here. And this guy is called the cystic duct. This is the cystic duct.
Yep.
And this is the next place that we see bile flow after the common hepatic duct. The cystic duct will then lead our bile to be stored momentarily in an organ that sort of sits as a blind pouch. This guy is our gallbladder. The gallbladder has one and one purpose only. This is the dude that stores our bile. This is where our bile hangs out until it's time to be released. So when bile just comes into our gallbladder and is just sitting there, what causes it to suddenly decide to leave and go somewhere else? As I'll mention in detail in a separate video, the hormone that causes bile to be released from the gallbladder is called, sort of a mouthful, cholecystokinin. Cholecystokinin, which is often abbreviated just CCK. And now this term might be a little crazy, but if you ever heard of the surgical procedure called a cholecystectomy, cholecystectomy, that's just the removal of the gallbladder. So cholecystokinin will cause our gallbladder to contract. And when the gallbladder contracts, remember, it's a blind pouch. So this is just going to squeeze all the bile that's just sitting here right back out to flow through the cystic duct and now go somewhere else. The next place you're going to have bile flow through is going to be another duct altogether. Now this guy is called the common bile duct. The common bile duct. And this is sort of the last part of the biliary tree we're talking about here. The last part of the biliary tree that conducts our bile until it finally reaches the GI tract. And the part of the GI tract that bile is released into is the duodenum. The duodenum, or the first part of the small intestine. In the duodenum, the bile is finally going to get to see some fat and start doing its job by emulsifying or making the fat easier to absorb. Now, the fat isn't absorbed in the duodenum. In fact, the bile salts with our new emulsified fat from our food will travel along to the ileum. Now, you remember the ileum is the last part of our small intestine. And this is where we're going to have our bile salts and our fats that were just emulsified absorbed. So this is where the absorption process occurs. The ileum is where absorption of our bile salts and our fats occur. The duodenum is where bile is secreted into the GI tract. So bile is secreted into the GI tract. Now, we talked about what happens to fats once they're absorbed in the ileum when we talked about the small intestine. But what happens to our bile salts? Well, the bile salts, after they've been absorbed in the ileum, are actually going to circulate right on back to the liver to undergo this process all over again. So if we were to review all the different pit stops that our bile takes in this process, number one is that bile is made in the liver. Then once it's made, number two, it's going to go through the common hepatic duct and then flow to the cystic duct to be stored in the gallbladder until we receive cholecystokinin as a signal to tell the gallbladder to contract. And then from there, bile is squeezed out of the gallbladder, re-enters the cystic duct. I guess you can say this is the fifth place it would go. Re-enters the cystic duct and goes into the common bile duct. The common bile duct is the last part of the biliary tree, which will then release its contents into the duodenum. And so finally, our bile has reached the GI tract. The bile salts will then do their job to emulsify the fats that we've eaten, and then we'll have our bile salts get reabsorbed in the ileum before it heads back to the liver, where it gets reused. So we reuse some of the existing bile salts in the liver. And that's how our biliary tree works.
Very nice. Thank you. I guess.
So the next organ we're going to talk about in our tour de abdomen is the pancreas. And I've drawn the pancreas right here. Let me just write that out. This is our pancreas, which I believe you may have heard about before. The pancreas sits below and behind the stomach, and it kind of hugs the first part of our small intestine here, which I think you may now recognize is called the duodenum. In fact, it wraps around a little more than what I've drawn right here, but just note that it sits back, way back over here. In fact, some say that the pancreas sits in a completely separate compartment from our stomach, our small intestine, our large intestine, even our liver. It sits not in the peritoneum. The peritoneum is where the rest of our guts sit. The
Hold on, buddy. Hold the phone. You up?
peritoneum is just a fancy word for the abdomen. So our stomach sits in our peritoneum, our liver sits in our peritoneum, the small intestine, the large intestine, all these guys sit in our peritoneum. But our pancreas is different because it sits in the retroperitoneum. And when we say retroperitoneum, that means it sits in the back of the abdomen. Now, it's not there alone. A lot of our big vessels that run through the abdomen are also there, the abdominal aorta, the inferior vena cava, these things you may have heard of elsewhere, but it sits. So the next
10, 7, 10, 10.
next organ we're going to talk about in our tour de abdomen is the pancreas. And I've drawn the pancreas right here. Let me just write that out. This is our pancreas, which I believe you may have heard about before. The pancreas sits below and behind the stomach, and it kind of hugs the first part of our small intestine here, which I think you may now recognize is called the duodenum. In fact, it wraps around a little more than what I've drawn right here, but just know that it sits back, way back over here. In fact, some say that the pancreas sits in a completely separate compartment from our stomach, our small intestine, our large intestine, even our liver. It sits not in the peritoneum. The peritoneum is where the rest of our guts sit. The peritoneum is just a fancy word for the abdomen. So our stomach sits in our back, way back over here. In fact, some say that the pancreas sits in a completely separate compartment from our stomach, our small intestine, our large intestine, even our liver. It sits not in the peritoneum. The peritoneum is where the rest of our guts sit. The peritoneum is just a fancy word for the abdomen. So our stomach sits in our peritoneum, our liver sits in our peritoneum, the small intestine, the large intestine, all these guys sit in our peritoneum. But our pancreas is different because it sits in the retroperitoneum. And when we say retroperitoneum, that means it sits in the back of the abdomen. Now, it's not there alone. A lot of our big vessels that run through the abdomen are also there, the abdominal aorta, the inferior vena cava, these things you may have heard of elsewhere, but it sits in this very different compartment. It's not there alone. A lot of our big vessels that run through the abdomen are also there, the abdominal aorta, the inferior vena cava, these things you may have heard of elsewhere, but it sits in this very different compartment. And in fact, to medical professionals, the pancreas is actually a force to be reckoned with for a couple of reasons. First of all, it releases a bunch of powerful enzymes that we're going to talk about in a minute. And these powerful enzymes can digest a whole bunch of our macromolecules, things that we eat, but also the things that line our cell membranes or make up other parts of our body. Not just in the retroperitoneum, but in the peritoneum, the thorax, everywhere else in our body. So it releases powerful enzymes. And two, the pancreas is a little strange in that it's unencapsulated, which is different from other organs like the liver. The liver's got the liver capsule. The kidney is covered by its own capsule. But the pancreas is essentially just a slurry of cells that's hanging somehow in the retroperitoneum. And that makes it a little difficult, especially for surgeons that have to operate nearby. You don't want to mess with the pancreas because it's got all these powerful enzymes that could cause a lot of damage around it if they were released. No wonder then the pancreas has sort of earned itself a special nickname. Many physicians consider the pancreas to be the lion of the abdomen because of how important it is, and additionally how powerful the enzymes are that come from it. So just like the lion in the jungle, You don't want to mess with the pancreas. So let's take a few minutes then and talk about what makes the pancreas so special. Physiologically, the pancreas releases two types of things, or has two main components to it. One, there's the exocrine pancreas. And the idea behind the exocrine pancreas is that it takes and behind the stomach, and it kind of abdominal minute. In the pancreas, is that their pancreas releases two types of things, or has two main components to it. One, there's the exocrine pancreas. And the idea behind the exocrine pancreas is that it takes salts and, write it down here, enzymes. So these powerful enzymes I talked about earlier. It takes these salts and enzymes and releases them in the duodenum, or the duodenum. I think you remember where that is. That's the first part of the small intestine, right after the stomach. And so our exocrine pancreas has four main roles that it accomplishes. So firstly, as you may recall, because the pancreas releases its contents into the duodenum, think about what the duodenum is receiving right beforehand. Well, as we talked about in the video on the stomach, we're getting a whole bunch of chyme that's been digested by gastric acid or hydrochloric acid. And so we'll need something to neutralize all that acid. And so the exocrine pancreas release bicarbonate. The bicarbonate here will serve to neutralize our gastric acid. So we will neutralize the pH, or the very low pH that we're receiving from the stomach in the form of gastric acid. And remember again, the gastric acid is hydrochloric acid. Next, as we move on, we'll talk about some of those powerful enzymes that we discussed earlier. One of them that the chloric acid. And so we'll need something to neutralize all that acid. And so the exocrine pancreas will release bicarbonate. The bicarbonate here will serve to neutralize our gastric acid. So we will neutralize the pH, or the very low pH that we're receiving from the stomach acid. Remember again, the gastric acid is hydrochloric acid. Next, as we move on, we'll talk about some of those powerful enzymes that we discussed earlier. One of them that we've briefly mentioned when we were talking about the mouth is amylase. And if you recall, amylase is responsible for the breakdown of starch. You remember, starch is just a whole bunch of carbohydrates stacked upon one another, and we break down starch into our smaller carbohydrates. So we'll just write smaller carbs for right now. So that'll include things like those glucose monomers or even disaccharides. And then another enzyme that we also release from the exocrine pancreas into the duodenum is something called lipase. Should be another throwback to the mouth because its name suggests that it breaks down lipids. So specifically, it'll take triglycerides, which I can draw here. So here's a triglyceride right there. And you've got these fatty acid chains that are coming off the glycerol head. It'll take triglycerides and it'll break them down into free fatty acids. And so those will look like this. So that's the acid part, and here's the fatty acid part, as well as things like monoglycerides. Monoglycerides look like this, and we're calling them mono because they've only got one fatty acid chain on them. We can also have diglycerides, which I think you might be able to guess what these guys look like. If I draw them out like here, diglycerides are going to have two fatty acid chains on them. There you go. And then it also will release glycerol. Glycerol. And glycerol is what happens when you get rid of all your fatty acid chains. And so you'll have some of these guys, and they're all OHs right here. So that's what your lipase will do, and it's similar to the lingual lipase that you had in your mouth. But in the mouth, it was mainly for taste when you digested your triglyceride. In duodenum, this enzyme works to break down triglycerides in a greater manner. And then finally, the last function of the exocrine pancreas involves its proteolytic enzyme. So I'll just write proteolytic right here. I'll expand. There are two types of proteolytic enzymes. There's trypsinogen that it releases, trypsinogen. There's trypsinogen, and there's also chymo. This is a longer word, chymotrypsinogen. Trypsinogen. And I think there's a couple of light bulbs that should be coming on right now, because whenever you see the suffix ogen, as we see down here, that refers to something that's called a zymogen. A zymogen, which means an enzyme that is inactive right now because it has an extra bond, usually a peptide bond, that needs to be broken in order for it to start doing its thing. So trypsinogen is the inactive form of trypsin, just like how chymotrypsinogen is the inactive form of chymotrypsin. And these guys need to be activated. And the way that's done is in the duodenum. There's an enzyme that sits there called enteropeptidase. There's a whole bunch of enteropeptidase peptidases that line the duodenum, your enteropeptidase will break down trypsinogen to form trypsin. Trypsin is the active form that's then going to be able to break down proteins. And what we're doing here is actually causing a chain reaction, because once trypsin is formed, the next step in activating chymotrypsinogen is accomplished by trypsin. Trypsin will cleave your chymotrypsinogen to form, this is a very long word, chymotrypsin. Chymotrypsin. And these guys will go wreak havoc and break down proteins in the duodenum. Now, my question to you is, these are enzymes and they're inactive because of usually a single bond. What happens when that bond that makes them inactive breaks? Say if you're in a car accident and you get hit in the stomach and there's enough force there that can provide activation energy to break a bond and turn trypsinogen into trypsin. What would happen?
What would happen? What would happen, eh? What happens is you're going to start breaking down more protein. Well, you can start breaking down more proteins.
Well, as we mentioned earlier, because the pancreas is unencapsulated,
You're gonna start eating up your own pancreas.
activated trypsin will go on to activate chymotrypsinogen into chymotrypsin, and then we'll break down proteins wherever they see them. And that can be membrane proteins. They could be proteins that are in the surface of the duodenum. They could be proteins that we digested in our food, or they could be proteins that are present in the pancreas. So you can see why the pancreas is so feared. And that's why the pancreas is something you don't want to have damaged, because we can activate these deadly enzymes that should be working in the duodenum.
What happened? Where'd he go? Oh no. Oh no.
All right, and then on that note, why don't we move on to the next part of the pancreas, which is known as the endocrine pancreas. And this is actually the part of the pancreas that is the most famous. We hear the most about this, as we'll see in a minute, because it has a lot to do with diabetes.
Oh, diabetes.
The endocrine pancreas will release hormones. Rather than the salts or enzymes we saw above, will release hormones that go into the bloodstream. And they will move on elsewhere throughout the body to the liver, perhaps the intestine, or even as far as muscles to cause things to happen. And the way the endocrine pancreas is organized is that there are many islet cells. It's actually pronounced islet, but I'm mispronouncing it just to let you know how it's spelled. Islet or islet cells that exist and sit in islands. Sit in islands. So there are three main types of islet cells we're going to talk about, and they're all present to some extent in each island or group of cells in the pancreas. And let's go through them one by one. So first of all, we've got what are called alpha islet cells. Alpha islet cells, and these guys release a hormone that's called
how you say it? I was gonna try to say it.
glucagon.
Jerk.
Freaking
jerk. Glucagon. You know, beta, I'm gonna get you. No, beta, insulin.
glucagon. And the main function of glucagon is to take things like glycogen, which is a whole bunch of glucose molecules that are stacked up on top of each other, and then break them down into smaller glucose monomers or molecules. So we're making glucose from glycogen whenever we release our glucagon. So we'll write glucagon up here. And it's not just carbohydrates, but glucagon is responsible for the breakdown of a whole bunch of macromolecules. So I'll just drive it home by writing glucagon causes breakdown over here. The next type of islet cell that we have, perhaps the most famous of them all, are our beta islet cells. So our beta islet cells house and release insulin. Now, when you hear insulin,
So what does this mean for the bloodstream? Chat? Anybody in the chat? No? Anybody in the chat know what we're talking about? Yes. Yes, you're right there. What do you think? Exactly. It means we're going to increase our blood glucose levels when we have a high concentration of glucagon. Right? Right. Yes. Break down increased glucose levels. Yes.
insulin, there should be a lot of
Insulin.
glycogen. Because insulin is responsible for a whole bunch of things. For one, when we look over here, insulin is what causes the opposite of this reaction, where instead of breaking down glycogen into glucose, insulin causes glucose to be stored or built up into glycogen. So insulin does the exact opposite. And again, to drive that home, it's not just for carbohydrates, but it's a whole bunch of things that get built up. So I'll write insulin is responsible for the buildup or storage of our macromolecules. What might be the most important thing to mention about insulin is that it is the hormone that is related to or responsible for the disease known as diabetes.
Diabetes
Gosh, we can have
mellitus.
entire tutorials on diabetes and what it does and what it means. But for right now, just know at its bare basics, diabetes occurs or causes damage to our bodies because we have too much glucose. Too much glucose floating around in our body, too much sugar, all right? And that happens because insulin is not working properly. We're not building up and storing glucose in glycogen like we're supposed to be doing. Instead, it's running all over the body. And because of that, we have what's called eye, nerve, and kidney disease. That's sort of the catchphrase we use in medicine to describe diabetes. It's eye, nerve, and kidney disease because with too much glucose over time, we're unable to see. The nerves, most commonly in our feet, are not able to sense pricks or things or damage that occurs there, and eventually they could cause amputation. And our kidneys stop working over time, which could lead to dialysis, and that causes early death. In addition to these three, glucose goes all over the body and causes a whole bunch of other things like earlier onset heart attack and other types of complications. The other thing I should mention about diabetes is that there are two types of diabetes. There are two types. There is type 1 diabetes, and there is type 2. And the way you differentiate type 1 versus type 2 diabetes is based on how it's caused. And this all points back to insulin. In type 1 diabetes, we have no insulin. So the person that has type 1 diabetes has no insulin production. And because of that, we're not able to store our sugar in glycogen. We're not able to put it away. And so we have it all over the place that causes eye, nerve, and kidney disease, among other complications. In type 2 diabetes, your insulin receptors, so you have insulin that's being produced, but your insulin receptors are broken. Your insulin receptors are broken, so even if we do produce insulin and it goes to where it's supposed to go in our body, these receptors will not respond. And so it's as if we don't have insulin in our body at all. And there's so much more that we can say here, but we'll close our conversation on diabetes for now, and we'll revisit this later. Let's move on to the third type of islet cell that we've got in the pancreas, and those are delta islet cells. Delta islet cells, these are the guys that release a hormone called somatostatin.
Somatostatin. Forgot about you. I forgot about you, somatostatin.
Somatostatin, which is the major party-pooping hormone released from the endocrine pancreas, because its main job is to stop the jobs of all the other hormones that are active. And these pancreas, because its main job is to, which is the somatostatin, which is the major party-pooping hormone released from the endocrine pancreas, because its main job is to stop the jobs of all the other hormones that are active. And these hormones can include things like what we've talked about here, glucagon, insulin, there are other hormones that are also in play in the GI tract that include things like cholecystokinin that we talk about elsewhere. And somatostatin will go in and cause the effects of those hormones to stop. And that's sort of its main role there. So that's our endocrine pancreas, and as we talked about earlier, our exocrine pancreas. So the pancreas is responsible for a lot. No wonder surgeons have the phrase, eat when you can, sleep when you can, and don't mess with the pancreas.
There you go. What else can surgeons say?
You're a surgeon for a lot. No wonder surgeons have the phrase, eat when you can, sleep when you can, and don't mess with the pancreas. So we've come a long way since we started talking about the gastrointestinal tract from our oral cavity. Now that we've
Twilight Zone. I feel like I'm in the Twilight Zone.
made it all the way down here, it's time to talk about the final part of our GI tract, the large intestine, or the colon, the rectum, and the anus. So let's zoom in and
I have
focus
to poop it out. I have to go poopy.
on what happens after we absorb our food in the small intestine. Well, it looks like our food passes into the large intestine, as you can see here. And keep in mind, when we call it the large intestine, that does not mean it's the long intestine. In fact, it's shorter than the small intestine we just passed through. It starts right here and continues on to about this point. The end of the small intestine is the ileocecal valve. The ileocecal valve. And that's the point where our large intestine begins. And this makes sense because remember, the last part of the small intestine is called the ileum. The first part of our large intestine is called the cecum. The cecum. And you can notice this little tail-like guy hanging out right here. This doesn't look like cecum. The small intestine is called the ileum. The first part of our large intestine is called the cecum. The cecum. And you can notice this little tail-like guy hanging out right here. This doesn't look like it does much, right? It looks like some functionless structure. And it
isn't that the Oh.
In fact, this is one of the most common
Oh,
causes.
wait, hold on. The appendix. Dang it. I was gonna say it.
Surgery in the GI tract. This guy is your appendix. That's the appendix right here. So this is the part where our large intestine begins. And just to finish up our roadmap, this part of the large intestine as it ascends upwards, called the right colon, but most specifically, we call it the ascending colon.
Yep.
This is the ascending colon.
Yep.
And it does exactly what its name suggests. It ascends upwards. It goes from the inferior point of your abdomen to a more superior point or above. And then we go this way. We run transversely, right? And so the part of the large intestine that continues on after the ascending colon is called the transverse colon. Another great name that describes how it runs, the transverse colon, because it runs transversely. And then next we'll get into this part here. If we saw this part ascending, then I guess we could call this part the descending colon. The descending colon. Great names here. Great names in the large intestine of the colon. This is the descending colon. So the descending colon does what it says. It descends. And then the last part of our large intestine, where we're not really descending anymore, but we're kind of flipping around like this, we're going upwards. You see sort of an S shape sometimes. There's an S shape that occurs. And so this last part is called the sigmoid colon. Sigmoid because it's got an S shape to it. That's your sigmoid.
Sigmoidal.
So what are the things the large intestine is most responsible for absorbing? Let's make this list right here. What does it absorb most importantly, and what's the impact of that? Well, the first thing you got to think about is water. Water is the main thing your large intestine is going to be absorbing. And it's very important for regulating sort of the output that we're eventually going to get from down here at the anus. Now, what would happen if we absorbed too little water? Too little water. Well, that would mean that our output would tend to be more watery, right? Because we didn't absorb that to our body. Now, that is what would cause diarrhea. Diarrhea, because you're going to have too much water left over in your stool. Diarrhea, right? Because we didn't absorb that into our body. Now, that is what would cause diarrhea. More plating sort of the output that we're eventually going to get from down here at the anus. Now, what would happen if we absorbed too little water?
I would think we had a hard poop.
Little water. Well, that would mean that our output would tend to be more watery.
Why would so we didn't absorb enough water? How does that make sense?
Okay, right? Because we didn't absorb that into our body.
Oh, I see. Okay, never mind. That makes sense. That actually makes complete sense. We didn't absorb it, so it actually has to be expelled out. So it's going to be diarrhea. I'll be back. Let's put the food away. Almost done. We got one more. One more lesson, hopefully. 1, 2, 3, 4, 5. One more hour, hopefully. Maybe. Maybe. I don't know. I don't know.
Okay? Now that is what would cause diarrhea. Diarrhea, because you're going to have too much water left over in your stool. Now let's think about the opposite case. What if we absorb too much water, right? There's too much water that's taken, so your stool is not as soft anymore. Water, as we can think about, is sort of the component of your stool that makes it relatively softer. So if we have too much water absorbed in our large intestine or in our colon, we'll get the opposite of diarrhea, right? So we're going to get constipation, which is not good either. And so the large intestine is very important for regulating exactly how much water needs to be removed. One of the other things that we can sort of mention at this point also is the disease known as cholera. I'm sure you've heard of this before. It's this terrible disease where you have a bacteria attack certain receptors or certain proteins that are on your intestinal lining, specifically in your large intestine. And what that means is you're going to start losing a tremendous amount of fluid, eventually leading to death by dehydration. And the interesting thing here is that if you can keep a person hydrated for long enough, amount of fluid, eventually in your large intestine. And what that means is you're going to start losing a tremendous amount of fluid, eventually leading to death.
Oh, means you're having diarrhea a lot, with cholera.
By dehydration. And the interesting thing here is that if you can keep a person hydrated for long enough, your GI will actually pass the bacterium out. So if you can keep a person hydrated while they have cholera, you can get them past the disease to be able to survive. The next important thing we should talk about that gets absorbed in the large intestine are inorganic ions. So inorganic ions, we talked about earlier when we discussed the small intestine. These include things like sodium or potassium. And remember, back then, sodium was absorbed as a co-transport mechanism with things like amino acids to help in their absorption. And so that occurs to a smaller extent here in the large intestine. Now, one of the interesting things that come up because of this, if you notice water and inorganic ions, things like sodium, potassium chloride, the large intestine is not the only place that it does that. Neither is the small intestine. In fact, the organ that's most responsible for the absorption of your water and your inorganic ions is the kidney. And so because of that, if we lost the large intestine entirely, if you had some sort of accident, or if you had a disease like Crohn's disease or ulcerative colitis, one of the treatments for ulcerative colitis is a total colectomy. So you remove the entire colon so you don't have that inflammatory process. And so you won't be able to absorb water or inorganic ions in your large intestine. But what that means is you still have the kidney. The kidney can still fulfill this function. Now, another interesting thing that I'm going to mention about the large intestine is that it's a rich source of microorganisms. Microorganisms like bacteria. So this gets a little weird because the question might be, why do we have bacteria hanging out in our colon? What's the purpose of that? Well, bacteria in our colon actually assist in the digestion of nutrients that we're not able to do because we lack those enzymes. They assist in digestion mostly of carbohydrates. This is kind of a significant process. You know, I read somewhere that about 5% of your output, your stool at the end, is composed of microorganisms like bacteria. And these are very important for digesting things like carbs. I'll put carbs here in parentheses. And oftentimes the byproducts you'll get of that are things like methane, CH4. And then the other thing is hydrogen sulfide, which you may not have thought of this way, but actually sort of explains a lot. Methane is something that causes a lot of flatulence. And then hydrogen sulfide is something that smells terrible. And one food that we often eat that gets a bad rep are beans that are pretty rich in carbohydrates that we're not able to absorb because we lack the enzymes. The microorganisms in our large intestine actually do most of the digestion of the carbohydrates that we have in our beans. So you probably heard that rhyme before, beans, good for the heart. The more you eat, the more you produce methane and hydrogen sulfide. All right, enough farting around. Let's talk about the last part of our GI tract finally. Now that we've passed through the large intestine, the next place we're going to go is the rectum. Now the rectum isn't responsible for any absorption or any breakdown. The main thing that the rectum accomplishes for us is storage. Now, we don't really think about it, but this is actually a very important part of our GI tract because once we've processed food and we've taken out all the water and now we've finally produced a waste product that we're going to take to the bathroom, we don't want it to come out right away, right? You want to hold on to it until it's a more appropriate time to expel that. And the rectum is key for this because it's going to hold on to stool until it's an appropriate time to get to the bathroom. What about the last part of our GI tract, the anus? Now, the anus itself is composed of two sphincters. As you might recall from our discussion on the esophagus, sphincters are just muscles that close off a hole. There are two sphincters that are responsible for the anus. There's going to be the internal anal sphincter, and there's going to be the external anal sphincter. The internal anal sphincter is composed of smooth muscle. The external anal sphincter, the one that's sort of wrapping around the internal anal sphincter, is composed of skeletal muscle. Skeletal muscle that we control. Smooth muscle is under involuntary control. So we have stool present in our rectum. It pushes on the internal anal sphincter. The internal anal sphincter will relax and open and allow the stool to move forward.
Cool.
Now, that doesn't mean that everything comes out right away because we have an external anal sphincter. This is something that's under our control. But then we finally get to the toilet, and it's time to relax that external anal sphincter and release food we ate in that first video. And finally that we've got here, man, do we feel relieved.
I need flush. Oh my goodness. Yo. All right. Yo. There we go.
Other than the brain, I'd say your intestinal tract, your digestive system, is one of the smartest organs in the body. Why is that? Well, the digestive tract has its own nervous system. It's got its own brain. In fact, we call it the enteric nervous system. The enteric nervous system, because the GI tract is able to act on its own without having to send neuronal information or signals to the brain or the spinal cord to regulate its action. For example, if we're in the presence of a really awesome meal, something that's good enough for any hero in a half shell, and we consume this meal and it goes through our mouth, the esophagus, and it lands in our stomach right here, and we've got our food right there, what we initiate from this, thanks to our enteric nervous system, is called the gastrocolic reflex. The gastrocolic reflex. That involves the stomach, the gastro part of this reflex, as well as the colon. Because what happens is that the presence of food in your stomach, as signal 1, tells the colon here it's time to make way for food that's coming down. So your colon will actually, as a response, take food that's in here and push it further south. And it does so to make room for the food that we're eating. That's the reason why after you eat, you feel like going to the bathroom. It's not because the food you just ingested is about to come out. It's because food that you ate a while back has come to the end of its journey, thanks to the gastrocolic reflex. So neuronal control is one mechanism our GI tract uses to control what we do when food is present. The other component we'll focus on down here is hormonal control. Now, hormones, as you might recall, are substances that are released by tissues in our body that then go through blood vessels, like this guy right here, to go to some target organ or target tissue to cause an effect. So I'm going to talk about a couple of hormones here that regulate our GI tract when food is present. So the first hormone we're going to talk about is called gastrin. Now, gastrin is a hormone that's released when we notice that there's food in our stomach. Gastrin is released out of the stomach to go to our bloodstream and then come back out, actually, to the stomach to stimulate the secretion of digestive juices. So recall that when we have food in our stomach is going to cause gastrin to be released from mucosal cells. The gastrin will then go on to cause secretion of a couple of things. One, you're going to get stomach acid or hydrochloric acid to be released from parietal cells in the stomach. You're going to get pepsinogen to be released from chief cells in the stomach. And remember, this is the inactive form of pepsin that must be cleaved to become active to digest protein. The other thing that gastrin does is that it increases stomach motility. Remember that one of the functions of the stomach is to churn food that's present. It's not just to release acid and pepsinogen that's going to digest food. It also physically breaks down the food. So we result in something that's called chyme. And I'll write that right there. Chyme is what the stomach sends to the duodenum. Now, gastrin release into our bloodstream is not unopposed. It's checked when the stomach acid reaches a pH of 3. When this occurs, then we're going to have a decrease in gastrin release. So low pH decreases our gastrin release. So I'm going to say red is inhibition, green is the go-ahead or the green light. So remember, the next part of our digestive process involves delivering chyme to our small intestine. And we'll specify the first part of our small intestine. And remember, that's called the duodenum. So chyme that's delivered to our duodenum. Now, this is going to cause the release of 2 other hormones. The first hormone I'm going to talk about is called secretin. So secretin. And I've sort of started the color scheme here. But once we have chyme delivered to our duodenum, secretin is released into the bloodstream. And it goes 2 places. So first, it's going to go down to the pancreas. That I could have drawn up here on your GI tract. It sits about right there in the duodenum. But I'm just going to write it out over here. So secretin in the pancreas is going to cause the release of bicarbonate-rich solution. So this bicarbonate-rich solution is going to involve our pancreatic enzymes. But the most important part that we want to focus on here is the bicarbonate. And why is that? Well, the whole stimulus for secretin release was the acidic chyme that was delivered to our duodenum. So of course we want to release a base like bicarbonate to neutralize that acid. The other place secretin is going to go from our bloodstream is actually right back up into the stomach. This is going to cause an inhibition of stomach motility and acid release and pepsinogen release, the kind of things we saw happen with gastrin. The other hormone that's going to be released because we have chyme in our duodenum, the acidic chyme in our duodenum, is called cholecystokinin. And as you remember, this is a hormone that's related to our gallbladder. And just like secretin, our cholecystokinin is released from our intestinal mucosa, so I can draw it coming from, say, here, into our bloodstream, and it's going to go 2 places as well. One, it's going to go to the pancreas to stimulate the release of our pancreatic enzymes. So release our pancreatic, I'll just write panc here, pancreatic enzymes. And this will help our digestive process. One of the enzymes that is released from the pancreas, that I'll explain in a minute, I'll help clarify things, is lipase. Remember, lipase is used to break down lipids, right? So that's what the LIP stands for. We're breaking down lipids. The other thing cholecystokinin is going to do is go through the bloodstream and arrive at our gallbladder. It's going to go to our gallbladder. And at our gallbladder, cholecystokinin is going to cause the gallbladder to contract. So contract our gallbladder. And what do you think happens when the gallbladder contracts? What's the main function of our gallbladder?
The main function is bile, stored bile. So if it contracts, that bile comes back
Well,
out.
remember, the gallbladder is holding bile that was produced in the liver. So when you squeeze the gallbladder, you're going to pump bile out of the gallbladder
Into
into
the cystic gut. That goes into common bile duct.
the cystic duct and down and out through the common bile duct into
The duodenum.
the duodenum. And that's going to help emulsify fat. And lastly, the other thing that cholecystokinin does is that it comes back here and decreases our stomach motility. We want to slow down the release of our chyme from the stomach because we need some time to process what we already have in here. Now, is it plain old chyme that causes our cholecystokinin and our secretin to be released into the bloodstream? Or is it something more specific in the chyme? Well, let me ask you, why do you think cholecystokinin was released? If we had to point to a specific nutrient that was in the chyme that requires then our gallbladder to contract and release bile and have our pancreas release an enzyme like lipase, what kind of nutrient do you think I'm suggesting here? Or
Lipids. Fat, right?
macromolecule. Well, if you said fat, you're absolutely right. It's the fat in our chyme that specifically causes cholecystokinin to be released. Okay, so what about our secretin? Well, again, this is up to you. Think about what's happening because of the secretin. The main thing here is that we're having bicarbonate be released. And so bicarbonate's a base, and we talked about how that's important for neutralizing our acidic chyme. So it's not really a macromolecule that causes secretin to be released. It's hydrochloric acid. It's the acidity of our stomach acid that's now delivered to our duodenum that causes the need for our bicarbonate-rich solution in the pancreas. So great. I think we have a good idea of how our GI hormones are helping us so far, at least in our intestinal tract. Now, I know that I gave a little shout out to the pancreas here. We separately talked about how insulin is released when we have an increase in glucose levels in our bloodstream to help us store that glucose for later use. And then the
To store it. So, yeah, that's insulin.
opposite occurs when we have a decrease or low levels of glucose and we cause glucagon
You want glucagon?
to be released to increase the amount of glucose then in our blood. Together, these hormones work in a very beautiful manner to make sure that we have the correct hormone to respond to the right stimulus so we can get food that just arrived in our stomach, processed all the way to the very end, thanks to our hormones, and as we mentioned earlier as well, thanks to our enteric nervous system.
Wow. Thank you so much, sir. We might just actually end it here, guys, to be honest with you. We do 12, 13, 14. I mean, maybe we could try to be finished with 18 tomorrow. That'll be the goal. But for now, I think we just do these two, and then then I have to work on the physio class. You. All right, let's take a quick 5 minute, and then we'll begin. We'll begin the quizzes. And then I want to do a quick exercise, a quick shower, and we will do physio, and then we'll add the Anki cards. We'll do the Anki cards after physio. And that's it. That wraps up the day. What a great day. What a great day. Put in work today, boy. Put in work. Put in work. I don't know if you guys really put in some work today. Yeah. Carbs. Yup. Look at that. I'm ready. This can be Freddy. They say, "Are you ready?" Aye, Captain. Oh, who lives in a pineapple under the sea? No, you're winning this first to me. SpongeBob SquarePants. Chat, what do you think? I might get this one wrong. Maybe. Because of sugar and has to do. Pepsin. Right? Yeah. Yes, sir. Maybe almost. Mm-hmm. Oh, wow, that's a good question, actually. I don't know what that one is. Damage to the mucosal layer. Possibly. Mm. I feel like we had damage to the mucosal layers. We got diffusion of the acid to the cells, destroying the cells. I don't know if that would mean we have an increase in stomach pH. I think maybe it's in this. I would say D. Ah. So then C. What the heck? What is a G cell? What? Oh man, I was completely wrong. What the heck happened, dude? What the heck happened, my dude? I don't know. Let's figure it out. So inhibition of the parietal cells. I thought not Chadlier's principle, maybe. pH increases as the sun becomes less acidic. Oh, really? Oh, it's literally okay. So I thought about it completely wrong. I was thinking it meant like it increased DHCl, not literally that the pH in the stomach. But I guess I just take it more literally. The liver. I went back to the duodenum. No, that's right. They do go back to the liver. I'm sorry. I think we're gonna go back to the liver. Well, probably start at the liver, right? I don't know if we even go to tissues. Honestly, trying to trick me, my dude. Don't let him. Don't let him. Excuse me, kind sir. Leptin, we don't even know what leptin is. Cholecystokinin, that's the CCK, I think. Or CCK, CCK. I think it's CCK. Gastrin. Pepsin. Pancreatic, huh? It's like which enzyme? Acidic in the small intestine. Oh, it is CCK. Okay, so CCK. Probably gastrin, I think. Oh, what the heck? Oh, sorry. Which one was not about secreting? If it's a high acidic small intense environment, that means that secreting is not in balance. We got low levels of secreting. Yes. The hepatic lobule is a structural functional unit of the liver. It collects blood draining from the hepatocytes. What the heck? So the corners have a lot of oxygenated blood. So zone 3, a branch of the portal vein, which each contain a branch of the hepatic artery, a branch of the portal vein, and a bile duct that carries. So it's not necessarily true, right? Well, no, actually, that is true. Oxygen-rich and nutrient-rich blood. Maybe. I guess not. Oxygen went through the lack of oxygen. Zone 1. What is the... I mean, this is just a little weird. Which one's which? A branch of the portal vein. Oh, okay. Okay, I think. I would be most susceptible to bacterial infection. I'm confused about that. Probably zone 1, right? Oh, okay. That's what I was just thinking. Yep. Okay. So we know that we can digest beta 1 for glycosidic 1 or glycosidic. And that has to do with more like cellulose, right? Yep. Resulting food is then excreted via nutrient exchange. Oh, and it's eat their own poo poo. Um, I would think the duodenum is the digestion, small intestine is the absorption, right? Sorry, jejunum, but that's all part of the small intestine anyways. We're good. The duodenum. Um, I'm gonna say lactose, right? What the mouth? Amylase? I see experimental. Oh well, technically not, because they're the wild type population, so they're the control group, right? That happens all the time. Oh, but they're the ones studying. I think they're the control group. Okay. I didn't see the large intestine. Oh shoot! Did the Sika? No. The stomach itself. Right. Yeah, we got 4 to 5. Still, not bad. Intro thingy. I mean, well, since the rest is just Anki, and I have to do the physio. I mean, we can just kind of end it here. Oh, yeah, end it here for now. But let me add the cards in. All right, thanks for watching, everyone. Thank you so much. Peace. I'm gonna keep going. Peace.